म्यूट करके स्टार्ट करना, ठीक है?
जब टॉप स्टार्ट होगी
म्यूट करके रिकॉर्डिंग में चलाते हैं।
रिकॉर्डिंग तो हो गया।
इधर ले लगाने एक बार पहले स्क्रीन कट कर लेना, लेकिन ये डबल टेप की गलती नहीं है। ऑन स्क्रीन नहीं अपना 10 मिनट तक मैं इस पे सिंगल नंबर आ रहा
हेलो
आप उस्ताद हो, आप करोगे,
जो
करोगे।
मैं गुड बेटा, मेरा डिपार्टमेंट का इवेंट है। इट्स ओके, इट्स ओके, डक हो गया। तो ठीक है, कट लेके
वीडियो तो कैमरा में रिकॉर्डिंग में जाएगी।
रात में कितना है?
ठीक है,
क्यों? अच्छा नहीं मम्मी तो मैंने कहना सीखा नहीं, सीखा तो नहीं सीखे।
सर जी अभी सर बुला रहे हैं आपको, तो कुछ नहीं करना। हमने तीनों वीडियो कॉल किया, केवल ये इसको करोगे तो ठीक है, सामने ठीक है। उसके बाद ये टैब से नहीं करते जैसे स्पीकर आएगा चला रहे हैं
अच्छा तब नहीं है।
ये पीडीएफ फाइल है।
चलो मैंने एक बार 10 तो इतना लेट हो जाना।
ठीक है,
मैं कहा तो इतना लेट हो जाना है।
कर दिया रिकॉर्डिंग। ठीक है, तो ये बीच में रोकेगा तो नहीं लाइट जाएगी
उसका कोई ना।
तो फिर तो सारा खत्म कर, एक बार लाइट गई तो को लॉग आउट मत करना।
मैं हमारा कहने का मतलब हमारा सेटअप चल रहा है।
हाँ
चल कोई ना
आगे वाली
रिकॉर्डिंग कर दे।
बस इसको पकड़ के रखो, आप इसको अब इसको सेट पकड़ के रखना भाई। कौन सी थी खड़ा रहे मैं भी नहीं, और नहीं पहले मेरे को कर देना है ना, बताओ उन्होंने मैसेज पहले मेरे को बोला ना पकड़ के रखे।
आपको ही बोल रहे हैं, हमारा तो काम है।
ये भी है।
चलो सर मैं चलता हूँ फिर, हमें ना पंगा पड़ जाएगा अगर कुछ ना समझ में आया। कुछ नहीं करना सर, ऑल्ट कुछ नहीं करना, फिर ऑल्ट टैब से कुछ नहीं करना, ठीक है। तो
उसकी पीपीटी चलानी पड़ेगी।
ऑल्ट टैब से
ओपन है ना, हाँ ओपन है, ऑल्ट किए ना,
ऑल्ट टैब करना है बस, और कुछ नहीं करना। जो फर्स्ट वाले की पीपीटी
मुझे लगता है
ठीक है।
इसको सेटअप करो सर, इसको परमानेंट लगाते हैं। पीपीटी तो पूर्ण कई होने किसी ने बंद कर देने का, किसी ने एक बार नहीं चला के शेयर करके देख सकता हूँ। मैं ये कह रहा हूँ सर, एक काम करो, जो खुलियां टैब वो बंद कर देनी किसी ने,
कौन बंद कर देगा गुरु जी?
आप ऑल्ट टैब से
कुछ बंद करने की जरूरत ही नहीं है, मैं कहने का मतलब ये है। चल तो
किस किस की पीपीटी है इसमें?
यार 3 एक तो ये वाली है।
हाँ तो त्रिपाठी सर की भी होगी, तो अभी वहाँ 4 पीपीटी आनी है टोटल।
अच्छा फिर करते रहो।
हाँ वही तो कह रहा हूँ। और क्या
आपकी पीपीटियां मंगा के लगाओ ऐसे यार।
तो मैं अपना
मेरी बात सुन, स्क्रीन दोबारा शेयर करनी पड़ेगी पीपीटी को।
नहीं वो स्क्रीन शेयर लगा देना, तो स्क्रीन जो है एक बड़ी।
ये
बस फिर तो ठीक है,
ये देख क्या कर रहा हूँ मैंने, बंद कर दिया, चल रही है ठीक है, बस आप खोल के चला
अनम्यूट करना, वो तो वो भी नहीं करना, म्यूट अनम्यूट करना कुछ,
अनम्यूट है
बस फिर कुछ नहीं करना, बस खोल करो स्क्रीन शेयर ही करना है।
अच्छा मैं आपको एक चीज बता रहा हूँ, वो जो संजीव सर जीवन की तो इधर,
हाँ ठीक है,
ठीक है, बाकी जो भी आएगा आप यहाँ पे कॉपी करना।
हाँ डेस्कटॉप पे कर लूँगा। हाँ ठीक है।
अच्छा तो अभी पहले एडवांस में लेनी चाहिए, ले लो मुझे तो।
एडवांस पे मंगा लो।
शशि की मन की डली हुई है तो ठीक है, फिर बाकी तो हम चाय की बेचने लगा लेंगे।
अच्छा चाय के बाद ही हो?
हाँ बाकी चाय की
ठीक है, वरना चाय में तो हम
आएगा ना फिर लगाया ना, और क्या कैमरा सेटअप हो गया।
ये ऑन है सर?
हाँ
ये माइक ऑन?
बोल के देख लो।
ना ना लग गई।
हाँ जी बोलो।
यही माइक ही कह रही थी क्या?
किधर गया
कोई नहीं, मैं से बोला हाँ ठीक है ठीक है, वो क्यों करता है नीचे बैठे रहो, होते रहिए यहाँ बंदे लोग। एक बार चेक कर लूँ।
माइक नहीं चल रहा।
अच्छा ठीक।
वो तो दस्ता है, चेक की करना है। नहीं चल रहा,
नहीं वो कुछ आता भी नहीं पाया
यार, एक तो प्रॉब्लम है इसकी ड्यूटी क्या है। वो कितने गए गोल्डी, कितने हो? ओ यार ये माइक तो ऑन कर देंगे यार, कितना ऑन होना
इसको टेप लगा के जा,
टेप है इधर
वो आ गई।
टेप
एक बार अभी कह रहा है, एक बार स्क्रीन देख ली।
रिफ्लेक्शन कैमरे पे पड़ेगा,
तो फिर जैसे स्पीकर वगैरह आएंगे ऐसे काला कलर दिखेगा।
जैसे होंगे
एक लाइट या फिर हल्की डिम कर सकते हैं, लाइट
लगा टेप।
लो भाई लगा।
ये एक दिन में नहीं होता सब, एक आवर्स में नहीं होता ये
बस
नहीं, बस नहीं गिरेगा।
नहीं
हाँ ना भाई
ये
कितनी अच्छी लाइट आ रही है, देख सामने देख, वहाँ देख, वहाँ भी इसको लग रहा है स्क्रीन पे।
एक और भी छोटी जी
ये लोग 144 का बिल है ना
18 रुपए के दिया
हाँ 18 रुपये का
ये जड़ा दिया
पहले जो दुकान में आप मिले
ठीक है सर
दुकान में बोलते थे
बस बस ओके
चाली है
ठीक है, स्पीकर दिखना चाहिए।
नहीं वो तो चल जाएगा कंपनी से
विक्रम सर, उन्होंने दिमाग में
अगर आपको घुमाना है तो घुमा सकते हैं
नहीं
पक्का हमको बता के ठीक है भाई
मतलब ये है कि हमने लेक्चर रिकॉर्ड किया, हमने किसी को दिखाना नहीं है।
ये यूट्यूब पे नहीं कर रही है
नहीं रिकॉर्डिंग करके यूट्यूब में बाद में डालेंगे, मतलब
एडिटिंग होगी वो
में डालेंगे।
कौन लाइव स्ट्रीम करते हो तुम
मैम देखने के लिए कौन है, किसी को तो दिखाने के लिए तो। चलो मैं कट कर भी भेजता हूँ भाई, ये रहना
हमारे
इन्होंने ये रहना
Good morning, one and all present. I request the students to kindly settle down in their seats. Our guests are on the way. Kindly settle down, please. Students are kindly requested to put their phones either on switched off or on silent mode so that there is no disturbance during the lecture.
नहीं अब आप थोड़ी तेरी आवाज सुनाई दे रही है।
वो बीच में बोलते रहो
नहीं माइक के आगे अनम्यूट करके बोलो।
I hope all of you have put your phones on silent mode.
किसने बच्चे बचना तेरा काम हो रहा है।
सर एक ना शमीम क्या जैसे कि ਜਿਹੜੀ पीपीटी दिखोगी उल्टी दिखोगी।
जूम चेक करना
हाँ
इसकी सही दिख रही है
ਤੁਹਾਨੂੰ ਸਹੀ ਦਿਖ ਰਹੀ ਹੈ ਨਾ ਜਿਹੜੀ ਰਿਕਾर्ड ਹੋਊਗੀ ਉਹਦੇ ਚ
ਕਿਵੇਂ दिख रही है
थोड़ा सा नीचे में रखो। हाँ, अब दिख रहा है।
वो भी बेचारी वही पूछ रही थी कि मैं खड़ी रहूं या
जब वेलकम करना होगा तब वो बोलेंगे, अनाउंस करेंगे जिसको वेलकम, जब वो वर्ड सुनोगे जाके वो पकड़ा सकते हैं ना। चेयर डालो।
वो पॉट्स कौन पकड़ा रहा है? वो किसने पकड़ा है? वो किसने वो पकड़ाने नहीं है? अच्छा ये वाले देने हैं।
जब आप बोलोगे वेलकम करिए वो पकड़ा देगा। ये भी यहाँ तो यार
फिर मैं अवधि ले लवाई
आपसे नहीं लवाई है पीछे तो समय सही नहीं ना जगह।
अच्छे
इतने लवाई हुई थी दूसरी
अच्छे अच्छे की सब
सब लोग हो रहे हैं ना
कितने आना है फिर
कोने में आना नंदिनी ने ऊपरों की थोड़ी आऊगी इन्होंने इतने लगवाओ फिर
सर बच्चे अंदर क्यों नहीं आएंगे? सारे पिटाई खा लेते हैं।
वो सुन लेना लेक्चर के बाद बोलना यहाँ अपने आप निकालेंगे कोई वीडियो वाला दे दो एक छोटा सा है वो एंड में देना, अगर दूध पूरी उससे पहले एक छोटा सा है ना, वो हम दे देंगे।
मुझे पहले बहुत पहले मैम ने बोला था कि मैं आते हुए मिस्ड कॉल कर दूँ, तो मिस्ड कॉल वाले को पता मैंने
मुझे भी अभी मैंने बात की है, चाय पी है
सर ऊपर कुछ नहीं बात हुई। सही गल है, वैसे आप ने खुलवा दिए अश्विनी सर्विस हाँ जी
I request all the students present to kindly give a standing ovation to our guests. our Honorable President, GGBSD College Society, Professor Anirudh Joshi, our worthy Principal Sir, Dr. Ajay Sharma, Registrar, Dr. Madhu Sharma, Dean Sciences, Dr. Sajeev Soni, our esteemed guests, my colleagues from various institutions, and my dear students. On the behalf of Bosons, the Physics Club, Goswami Ganesh Datta Sanatan Dharma College, Chandigarh, I extend a very warm welcome to all of you for the 5th National Seminar on Recent Advances in Material Science in collaboration with Institution Innovation Council, IIC. I would firstly request the dignitaries present on the dais to kindly present a green welcome to our Honorable President, Shri Anirudh Joshi ji. I would now invite our respected Professor Joshi to kindly say a few words and inaugurate the event.
Honorable Professor Dhiman, most honorable guests from Himachal and from my university, Professor Tripathi, other esteemed guests. आज इस लड़की ने बड़ा गलत आदमी चुन लिया। मैंने फिजिक्स पढ़ी नहीं, लगभग 4 दशक तक संस्कृत पढ़ाता रहा। मुझे फिजिक्स सिर्फ इतनी आती है कि एक मैटर होता है, एक एनर्जी होती है, दोनों का रिलेशनशिप स्टडी कर लो तो फिजिक्स आ जाती है, पर मैथमेटिक्स आना चाहिए, इक्वेशन मैथमेटिक्स की। मैं संस्कृत का स्टूडेंट रहा, मैंने आपको बताया। ऋग्वेद में एक मंत्र आता है, मंत्र अन्न के लिए, उसका पहला शब्द है ऊर्जम देहि, ऊर्जन नो देहि द्विपदे पुष्पदे। भगवान हमें ऊर्जा दी। जिस दिन ये इंसान धरा पे उतरा था, उसे आसमान दिखा, उसे सितारे दिखे, उसे चांद दिखा। उनकी शक्ति से उसमें ऊर्जा आती थी। वहीं से एस्ट्रोफिजिक्स शुरू। वो पर्यवेक्षण उनको देखने का, जब ऊर्जा मिलती थी, उन्होंने देखा वनस्पति उग नहीं सकती अगर सूर्य की ऊर्जा ना हो, सौर ऊर्जा ना हो। तो उन्होंने ऊर्जा का अध्ययन करना शुरू किया। मेरा ख्याल है फिजिक्स वहीं से शुरू। अब फिजिक्स वालों ने एक बड़ा और काम कर दिया, जहां भी ऊर्जा देखी वहां अपना झंडा काट दिया। हमारे शरीर में ऊर्जा कैसे पैदा होती है, जब हम खाते हैं उससे ऊर्जा कैसे, एनर्जी कैसे पैदा होती है, और वो कहाँ जाती है, कैसे काम करती है, इसका नाम बायोफिजिक्स रखा गया। एस्ट्रोफिजिक्स के साथ साथ एक और बड़ा चमत्कार होगा। जब चांद और सितारे देखे तो ऋग्वेद में एक फैक्टर वर्णित हुआ है जिसे हम कहते हैं हिरण्यगर्भ। ये फिजिक्स वाले उसे कहते हैं बिग बैंग थ्योरी। हिरण्यगर्भ का सिद्धांत था कि एक विस्फोट हुआ प्रकृति में ईश्वर की आज्ञा से। फिजिक्स वाले तो पता नहीं मानते हैं ईश्वर को कि नहीं, ऋग्वेद वाले मानते हैं, मैं मानता। तो उस विस्फोट से जो जितनी शक्ति थी, ऊर्जा थी, वो अनेक खंडों में बिखर के समस्त ब्रह्मांड में जा गई। ये बोसोन का एक्सपेरिमेंट जिसमें मेरे 2-3 कोलीग बहुत, सुरेश बैरी और दूसरे लोग रहे, तो वो ऊर्जा थी, उसका ध्यान भी भौतिक शास्त्र यानी फिजिक्स वालों ने मैटर हो गया। अब ये मटेरियल भी नहीं छोड़ना चाहते कि कोई चीज को छोड़ दो, बोतल आपको एनर्जी देती है कि नहीं देती, ये तो छोड़ दो। फिजिक्स वालों, आपकी माया मैं नहीं समझ पाऊंगा, आप समझिए, इन विद्यार्थियों को समझाइए। आपका स्वागत है।
It's always a delight to listen to Professor Joshi, and same has been the case for today also. We are actually delighted to listen to you, sir. I would now invite our worthy principal, Dr. Ajay Sharma, to kindly address the audience.
Honorable Professor Shashi Dhimman, Vice Chancellor, Himachal Pradesh Technical University, Professor Anup Joshi ji, President GGBST College Society, Professor Ravi from IIT Hamirpur, Professor Tripathi from Punjab University Chandigarh, my learner colleagues from the Science and Allied departments, and dear students. It's a great day today that our department is organizing 5th National Seminar. So it speaks high about their academic rigor and contribution that regularly they are organizing the seminars for the betterment of the students and faculty alike. Our college is NAAC A+, having college with potential for excellence, star college status from Department of Science and Technology and Department of Biotechnology. And one of the key contributor in this area is Department of Physics. We are not only running the courses at UG and PG level, now we are also running the research center in the area of physics. And hoping that we will be now pursuing more towards the research area and have the more contribution in this academic field. So such type of interactions, seminars are helpful to all of us. Not only it opens the eye for our old colleagues, it also opens up the eyes of the young students. What is happening in the area? So this seminar hopefully will be enlightening all of us in the area of recent advances in material sciences. Because normally we feel that our syllabi and universities are not updated regularly. So there is a great scope between what we are teaching and what is happening. And such seminars and interactions are in a position to bridge that gap. So I congratulate all the organizers for the event and welcome to all the speakers. And I will request all the students to be interactive, ask the questions so that you are in a position to have maximum benefit of the presence of such eminent personalities. Thank you.
Thank you so much, Principal Sir. We truly appreciate your constant support and encouragement, which motivates us to keep on organizing such seminars and events. I would now invite our HOD, Dr. Neeru Mahajan, to kindly say a few words about our department.
Good morning, all. I welcome you all to the one-day national 5th seminar on the behalf of the organizing committee. It's a matter of great pleasure that Department of Physics, Swami Ganesh Datta, Sanatan Dharma College is organizing 5th national seminar on recent advances in material science. I would like to express my deepest gratitude to Honorable President Sir, worthy Principal Sir, respected Madhu Ma'am, and respected Dean Sciences for their consistent encouragement and support. I am delighted to welcome our guest of honor, Professor Shashi Dhimman, Vice Chancellor, Himachal Pradesh University, and my sincere thanks to the eminent speakers, Professor Ravi Kumar from NIT Hamirpur and Professor S.K. Tripathi from Punjab University for sparing their valuable time and sharing their research work with all of us. At this special moment, I would like to take an opportunity to present a brief overview about the department. The Department of Physics was established in 1979 and is one amongst the basic science departments at GGBST College. The Department of Physics was conferred with the status of research center by the Punjab University in 2017. Our department has the strength of 13 experienced faculty members, and we offer various programs, BSc Physics, MSc Physics, and PhD. The department has established high standards in teaching and research of both basic and applied physics, such as particle physics, condensed matter physics, nuclear physics, plasma, and non-linear dynamics. We have presently 13 research scholars who are pursuing their doctoral work with the department. On the behalf of the organizing committee, I welcome each one of you to the one-day national seminar. This seminar will share an insight into the recent research areas and various opportunities for carrying out research in material science. Thank you all.
Thank you, ma'am. We are honored to have with us Professor Shashi Dheeman, Vice Chancellor, Himachal Pradesh Technical University, as our keynote speaker. Firstly, I would request the dignitaries present on the dais to kindly present a green welcome to our esteemed guest. We are also honored to have with us our guest, Professor S.K. Tripathi from the Department of Physics, Punjab University, Chandigarh. I request the dignitaries to kindly present a green welcome to Professor Tripathi. We also have with us Professor Ravi Kumar from MIT Hamirpur. I would like to request, please present a green welcome to Professor Ravi Kumar. Before we begin with the keynote address by Professor Dheeman, I would like to take this opportunity to introduce Professor Dheeman to our audience. Professor Dheeman has been the founder Vice Chancellor of Himachal Pradesh Technical University, Hamirpur. He has completed his PhD in the field of nuclear sciences and has been a professor of physics at Himachal Pradesh University, Shimla. He has published over 100 research papers and review articles in various journals of international and national repute. He has guided 54 research scholars for their PhD and MPhil degree thesis. He has also acted as principal investigator for many research projects. He has also held permanent teaching and research positions with various institutions of eminence, such as Indira Gandhi National Open University, Delhi, School of Physical Sciences, Jawaharlal Nehru University, Delhi. And he was also acting as a director, University Institute of Information Technology, and president's nominee at Rajiv Gandhi Central University, Arunachal Pradesh. He was a member, Governing Council, Board of Governors, Inter-University Accelerator Center. He has visited many university and higher educational institutions in India and abroad, such as the Institute of Nuclear Theory, University of Washington, Seattle, USA, as a visiting professor, and the University of Birmingham, UK, as a visiting scientist. His current research interests include development of nuclear density functional theory based on effective field theory, atomic nuclei, hypernuclei, compact states of astrophysical interest, quantum computation, and information technology. We are truly delighted to have you with us, sir. I would now invite Professor Dheeman to kindly come on the dais and deliver the keynote address of the event. Professor Dheeman, please.
Clear? जब मुझे चाहिए होगा तो फिर प्रश्न आपको बुलाऊंगा, ऐसे रखो। सबको नमस्ते मेरी तरफ से। सभागार में बैठे सभी लोग, डॉक्टर अनिरुद्ध जोशी, प्रेसिडेंट
GGBST College Society Chandigarh, Dr. Ajay Sharma, Principal SD College Chandigarh, Dr. Sanjeev Soni, Dr. Madhu Sharma, Dr. Neelu Mahajan, my distinguished colleague, Professor S.K. Tripathi, Punjab University Chandigarh, Professor Ravi Kumar, NIT Hamirpur, and Dr. Sanjeev Kumar, who is associated with me since the day I first visited your college a few days back. So at outset, I would like to thank Principal Ajay ji for inviting me for a small interaction with enlightened group of SD College. So thank you very much, Dr. for giving me an opportunity to interact with all these young people. तो आप सबने सबसे पहले आज एक संस्कृत के विद्वान का बीज भाषण सुना। तो साइंस का जो हमारे भारतीय संस्कृति में एंशिएंट टाइम से वेदों में या कहीं भी सूत्रों में, कहीं भी किसी भी उपनिषद में, वेदों में, कहीं भी सूत्रों के द्वारा ही उसका निर्माण हुआ। जैसे आप आजकल किताबों में पढ़ते हैं ग्रेविटेशनल फोर्स फॉर एग्जाम्पल, तो इंग्लिश में लिखा होता है, हिंदी में उसको गुरुत्वाकर्षण बोलते हैं। और वो गुरुत्वाकर्षण तो एंशिएंट टाइम से ही भारतीय संस्कृति में भारत के ऋषि मुनियों ने आविष्कार किया था। तो जैसे एनर्जी का इन्होंने बड़ा अच्छा एग्जांपल दिया कि बिग बैंग थ्योरी वी टीच एवरीबॉडी नाउ, बिग बैंग थ्योरी इन क्लास। I being a man of astrophysics, I used to teach in my class. I am basically taking course on nuclear and particle astrophysics in National University. So I have designed in a way that I am teaching little part of my ancient contribution, and then I take that forward through the Big Bang theory to the nuclear reactions which are occurring in a stellar medium. तो आप सब लोगों को जो साइंस आज की एज में जो यंग लोग हैं, आप सभी जो साइंस को, फिजिकल साइंस को आप अपना प्रोफेशन बनाते हैं, तो आप संस्कृत जरूर पढ़ें। संस्कृत से क्या फायदा होगा कि आप अपने एंशिएंट साइंस कंट्रीब्यूशन को अंडरस्टैंड करके उसको अनफोल्ड करेंगे समाज के लिए, और सिर्फ भारतीय समाज के लिए नहीं, पूरी दुनिया के समाज के लिए। जैसे फॉर एग्जांपल अभी ग्रेविटेशनल फोर्स का ही मैं आपको एग्जांपल दूं तो भास्कराचार्य हमारे एक बहुत बड़े सेंट हुए, उन्होंने सूत्रों में बांधा है गुरुत्वाकर्षण को, और उस सूत्र से ग्रेविटेशनल यूनिवर्सल ग्रेविटेशनल लॉ एक्सप्लेन होते हैं, मोशन के ऑल थ्री, and they are very universally. You go to any part of the imaginative universe, we claim that there are thousands of millions of billions of universe, and billions of stars, billions of planetary systems, and galaxy and so on. If you believe in that, then you see that gravitational force is valid everywhere. That's why it is a universal gravitational force. तो भास्कराचार्य जी ने इसको संस्कृत के सूत्रों में बांधा, मगर मे भी आज से 5000 साल पहले। तो वो लिटरेचर है, अवेलेबल है, वो सूत्र भी अवेलेबल है, और उस सूत्र का अनफोल्डिंग अगर समय से पहले हम करते तो जो मॉडर्न एज का सबसे महान वैज्ञानिक हुआ वो भारत में ही था, जिसको न्यूटन बोलते हैं। न्यूटन के नाम से, न्यूटन was also great, says he was unmarried, and he was basically is a man. You see, if I narrate one story to you, once in a conference, Gamow is a Nobel laureate from Russia, and Dirac. So Dirac is a very young guy at that time. The meeting was, I think, conducted in Germany somewhere. So he was asking that everybody is saying that Einstein is great, Einstein is great. Where you and me stand? Then Gamow, you see, being a mature person, he told that in our century we get one Einstein, and in the 4th century we get one Newton. Now you evaluate where we stand and where I stand. You see, all of them are great physicists of the time, but the contribution who make that matters. Okay, the contribution of Newton's, we feel that maybe more and more superior than the contribution we or my generation or your generation is making. But if you go to the Indian ancient science, then you'll find that our civilization was far, far ahead. So it's the one thing you should note. And there are evidence. Now you see, worldwide people have accepted that the zero number was invented in India. But why should our ancient states should invent zero only? Why they are interested in inventing zero? This means that the entire neural system was invented by them. Only the zero useful, because electronics was not there at that time. Otherwise, they would have done a lot of electronics and there is 0 and 1 state. So binary system has to be explained to the society, and you require only 0 and 1 knowledge. There's nothing required other than this. But you see, at that time, 0, if we invented, that means we have invented the numerical system entire. And there are evidence, as Dr. Joshi referred to the astronomy. You see, our ancient scientist was very much skillful in measuring the astronomical object at that time, astronomical distances. They know accurately the distance between sun and earth, the position between sun and earth, the relationship between sun and earth. In modern science, people just now, maybe 500 years ago, they understand that sun is fixed. Before that, they feel that this is totally system different and earth is controlling everybody, every planetary system. But it was not true. But it was known to this civilization before. So, आप सबसे मेरा आग्रह है कि आप लोग भारत के जो एंशियंट टाइम के कनाल जैसे केमिस्ट्री में डाल्टन गेव थ्योरी few hundred years back, मगर उनसे 2500 साल पहले कनाल जी ने थ्योरी लिखी थी. He made a principle about the atomic structure. What is the atomic structure? It's a center which is very heavy. The light particles are in a fixed orbit, like sun at the center, and planets are moving around. Okay, so that is the analogy he draw, and you see, construct the principle that is available again. It's a very famously available in Sanskrit literature. So, what the idea is to build up a vision which has a full world view. मतलब आपको जो आइडिया अपना फ्यूचर में बनाना है वो बड़ा होना चाहिए. You should be capable of thinking big. And this is the age where you can think of doing something big, which you may or may not be ignoring, but you are conceiving the idea and you are going ahead and you are ready to sacrifice whatever time, energy is required. So this is what is the inspiration you can have from, our ancient science. So you must study ancient science, and if you wanted to have a first understanding of ancient science, then you must know the Sanskrit. So Sanskrit language is this important. Okay. So recently, as said that I am in technical university. In technical university also, I have started one center, Adhyan Kendra, Sanskrit Adhyan Kendra. And right now it's a very primitive stage, but the idea of that Adhyan Kendra is कि वहाँ संस्कृत के एक स्कॉलर हैं, वो हमारे बच्चों को संस्कृत में बोलचाल सिखा देते हैं. And that fellow is so skilled that within a week you will be able to identify what is this. किताब को क्या बोलना है, पेंसिल को क्या बोलना है, रोटी को, कपड़े को, कमीज को, दोस्त को. तो जो फंक्शनल वर्ड्स हम इंग्लिश में या हिंदी में एक दूसरे के साथ प्रचलित भाषा में यूज करते हैं वो सिखा देते हैं. They are so skilled. So this is basically the scheme of Government of India. They have central university created at Delhi, and they have regional colleges, I must say, which we have in Himachal also. So they have created it in a technical university. In a technical university, you imagine the teaching of something. So how this is important is at this point of time. So now if go beyond the modern view of science, as I explained one example, that is the Newton, and there is a story about it. But we have to see that where we forget about the knowledge our ancient people has created, where that was left, and the civilization as a whole becomes ignorant. And that basically begins with the invasion. Our country was invaded by various races from west or east, wherever. And very recently it was by the Britishers. They created colonies here and they started ruling our country. Okay, so basically they also use science as a medium to loot our wealth. Okay, that's why first of all they created Survey of India. If you go to the website of Survey of India, you'll be surprised to know that why we created Survey of India, why it is required. Nowadays, Survey of India, same Survey of India is continuing and doing same job. But why they require at that time? They require at that time to understand the entire system across the nation. In what form the wealth is available. For example, agriculture. Which area of the country is growing what kind of species, which are very useful for the health. So let's ask the people to do that agriculture and take away the material to UK and use for their own people. So that is one example. Another is they created Survey of India to go to far flung areas, know about the weathers, know about the vegetation, and know about the materials which are available through mining, maybe gold, maybe copper, maybe anything else. Maybe you have a temple now. If I have to locate temple somewhere in Kinnaur, I require some person who can go there and locate that. So I cannot go because I don't know anything about Kinnaur. But I have to find out some local person, recruit him, and take him away to the Kinnaur where the temple is there. And there I can find out that that temple has used wealth, because you see जो हमारे लोगों में विश्वास है वो टेम्पल में है, और जो घर में भी हमारे नहीं रख सकते हैं उसको टेम्पल में रख देते हैं. जो सोना हम घर में नहीं रखेंगे टेम्पल में दे दिया. So they use Survey of India to loot us. And they looted India to the extent that in 1947, our people were hungry. There is no agriculture, because whatever our ancestors used to produce in the field, they take up. Maybe 5% they leave to them. तो उन्होंने डिसाइड किया कि इससे इसको पैदा ही मत करो, एग्रीकल्चर ही बंद कर दो. And you see, Joshi Saab is the oldest person around us. He can tell that the position in 66 is food scarcity. Which is the result. But afterwards, now we have come up, we have surplus food, we are supplying across the world the food, all articles. So this is one example. I'm citing that the heritage of science in India. And you see, if you look at the contribution of scientists during the freedom struggle, then that also you can name so many people. For example, B.C. Roy is one of the chemistry professor who started Bengal Chemicals. Still that company is working. That is the beginning of industrialization, you can say, during the during this era when they are going to end it in India. And you have J.C. Bose. He's a man of wireless science and he understands botany also. How the life in a plant is different than the human life, or how it is same as the human life. Okay, so that is, he's the pioneering man. And your 5G technology depends upon totally based on the principles of J.C. Bose. He did this work during the second decade of last century. So what I am trying to share with you that you being a young mind and you born in a free India and prosper India. So genetically also you are more superior to think freely. There is no insecurity. There is no any sort of things which are imposing you the constraint not to think freely. You think freely, get good training in science, and if you think of something big, always. So, if I give one more example of science, then you see we understand the forces. Okay, gravitational forces. Just now I make a easy comparison with this, and now we are in a position to understand reasonably very well the nature of gravitational force and its industrial applications. Once we are able to understand gravitational force, then there is a locomotion. All mechanics is the application of that. Potential energy, usefulness of potential energy, as we understand, all of us understand. But we understand this gravitational force also because Einstein's theory of relativistic general relativity is kind enough to help us to understand gravitational force. Likewise, we have electromagnetic force. So once we are able to understand that, then that has a very nice industrial application in light energy. We are now sitting in a well-closed hall only because of the light which is available, and which you see is generation of this light begins with the understanding of electromagnetic interactions. So there are so many examples I can cite the industrial applications of electromagnetic, like your digital communication, whatever right now we are doing. And another is nuclear forces. For example, we have a weak force and strong force, and only because of the understanding of nuclear forces, you can think of why we are getting light from sun. Why sun is emitting light? You see, the light which is now reaching you from the surface of sun has been created through the fusion reactions a million years ago. So there is a fusion. I think all of us understand. Since I understand that all of you are graduate students, so there is a proton-proton fusion. Okay, so there is a synthesis of another isotope of hydrogen and emission of beta particle with some energy and a neutrino. Okay, so that energy, that radiation created during the process of fusion energy, or during the process of as a fusion energy in the core of sun, you see, take millions of years to travel to the surface. Once it is on the surface, that radiation reaches to you as a light. So it carries so many other things also, cosmic rays on the way, but you see the umbrella or the structure of Earth is such that it saves you from the direct light from the sun. So this is basically the understanding. You can understand that why sun create energy, why there is energy in the stellar medium. So these forces of nuclear physics can enable us to understand that. Okay. And this in terms, you can say that now these forces, electromagnetic interactions and the nuclear forces are well or very nicely explained with the help of quantum theory. So quantum theory also gives us, as you see, so many things like your laser technology. You can have or whatever. Now you're going to listen my distinguished colleagues also. So whatever material they are going to share with you and their applications, you can understand with the help of theory of quantum mechanics. Okay, so now these two theories are enabling us to understand nature, and nature is being, you see, described by the fundamental forces and the fundamental particles. Okay, so with these words, I will now stop here. But again, the request to all of you to make a view which is wider, okay, and enter into the regime where there are challenges. And if you go to any other area other than science, then definitely choose entrepreneurship, where you can provide, you see, provide your services to the society directly. Okay. So thank you very much.
Thank you so much, Professor Deen, for inspiring our young minds through such an interesting talk, bringing up the connection between modern physics, ancient physics, and the significance of studying science in today's days. I would now invite our respected Dr. Madhu Sharma to formally thank Professor Deen.
Good morning, everyone present today. Foremost, I must admit, in all my humility, I find it to be an extreme privilege to be a part of a scientist gathering. I am from Department of English, as most of you might know, so I have never been really into any kind of seminar where such eminent scientists and researchers will be participating, and they will be sharing their views primarily in an inaugural session. When we take an overview of the situation, what Professor Deen is telling us is something wonderful. What we look at today is that change is the only thing which is considered constant. And anyone who does not keep abreast of our times is lags behind. And in order to change, first of all, we have to accept and acknowledge the change, and then we have to gear up, prepare ourselves to go ahead with the change, with an adaptation. Whatever has been there in our scriptures, in our mythologies, in our sutras, Vedas, etc., of course, it becomes some kind of duty for the Indian community to take it forward. Both Professor Joshi and Professor Deen have rightly pointed out that this becomes mandatorily important for the current generation. As Professor Deen rightly pointed out, that you are a privileged generation. You are genetically superior. I would call it a genetic lottery for you. A few days back, in fact, I was teaching a chapter on partition times of India. So compare ourselves. This has not been a long back. Your parents, your grandparents must have known about those times, and they have the first-hand information and experience about that. Look at where we are positioned today. How fortunate we are. We are born in a free India, and we have all the privileges of education, enlightenment, resources available to us. So it becomes our duty to take the baton forward, right? And besides this, I would congratulate the organizers for such a beautiful session and such a beautiful seminar, which is going to be useful. Definitely all academics require updating from time to time, which comes from fruitful deliberations and presentations that we are looking forward to in a session like today. Thank you very much, everyone, to be here. My special thanks to the dignitaries on the dais, including Professor Deen and the other expert speakers. Thank you very much.
Thank you, ma'am. I would now request the dignitaries present on the dais to kindly present the token of honor to Professor Deen. Thank you so much. We would now break for 15 minutes. The tea for faculty members is being served outside this auditorium only, while students are requested to move downstairs. Volunteers are there, they'll guide you to the place. Research scholars are also supposed to join us outside the auditorium. Students, kindly keep your seats for a minute. Let the dignitaries go out of the hall first. Kindly be in your seats, please. There will be volunteers. They will guide you to the way. We'll be meeting after exactly 15 minutes.
ये पेन ड्राइव से प्रेजेंटेशन चला के देखनी है पार्टिसिपेट
Those are volunteers, kindly guide the students to the place for tea so that we come back in time.
फोल्डर है फोल्डर है
You have to go to the lawn from this gate. This is the gate. The gate to the left of me. You have to go to the lawn.
फर्स्ट फोल्डर है
यही है जल्दी है
टॉपिक है रोज हाँ
यही है दूसरी वाली भी बोल रही थी कॉपी ऑफ लिखाना नहीं नहीं पेन ड्राइव से पीपीटी चलाना जो चलानी है ना पीपीटी चला पीडीएफ में
चल रही है
ठीक है सर पेन ड्राइव लगे होंगे 11 बजे अगले सच चाहिए बंदा
म्यूट हो यार यहाँ पे कुकिंग वाटर लीक कर रहा है, वाटर लीक कर रही है, ऊपर नहीं रखना। तो यहीं पे ना स्टेज पे ड्यूटी है ना, पता है क्या करना, ये बॉटल्स को या तो यहाँ पे कॉर्नर पे रख लो, वहाँ सारी स्टेज पे नहीं जानी होती है यार, कई बार ना इधर से लेके जानी पड़ती है बात को, तो फिर वो उधर से उठा के नहीं लेके, तो ये कॉर्नर पे रख लो इनको।
मुझे सच में अपना अपना बंगाली नटी लग रहा है।
आज वैसे थोड़ा सा बंगाली लुक दे रहे हो।
दे रही हूँ ना यार, काला जादू बंगाला।
अरे वो नहीं, इट्स बिकॉज ऑफ दिस।
बिंदी ना, है ना, मैं लगाती नहीं हूँ बिंदी यार।
आप तो वैसे भी इयरिंग नहीं डालते
हाँ
यार, पीछे तो हुआ लिफाफा, खड़े हो जाओ आप। कहाँ माइक पे?
Where should I look? Where should I look?
बस मेरा देखो।
तेरे फोन चली गुलाबी चमकती है,
बड़ा अच्छी लगती है यार। ओ पवन पवन चलो फोन करना।
काम के लिए बोला चाहिए
साइकिल लिया हमने, साइकिल लिया हमने।
उसको पूछो।
मैं तो पी लूंगा भी।
तुमको लंच पे आएंगे, अब आप मेरा नाम लो।
11 बजे जो चाय का टाइम है वो यही 2 बजे
डिपार्टमेंट के
बंदे का पानी अभी बंदे ने पानी अभी पीना आपके 4 बजे पानी पिलाएंगे। आ रहे हो वो लैब लोग करके आ रहे हो।
फिर ऐसे थोड़ा सेल्फी का हाथ पड़ा थोड़े बंदे रखे हुए हैं। बढ़िया तेरे बढ़िया आएगी इनको देखो
लाइट नहीं अच्छी पड़ रही हमारे यहाँ थोड़ी बहुत सारी एग्जाम है।
बस हम अच्छे हैं, हमारी अच्छी आएगी। यार आज भी क्या हुआ? जैसे जैसे मेरे साथ लेट हो गई थी दूसरे के ये भी बता रहा अपने नहीं वो भी हो गया तो दे रहा है बस एक पैकेज हो रहे हैं वो नहीं पता पेपर चल रहे हैं
पीछे है बट
कॉपी हमें भी दे दो
क्यों पता नहीं
ऐसे
you have to earn it
हम अर्न कर लेंगे
you earn it 10 रुपए कर दो हो गया हाँ 100 रुपए कर दो 200 रुपए की ट्रॉफी
बस 100 रुपए की अर्न करनी है
200 ट्रॉफी है
मैम 2 बार वेलकम हो गया
किसका
उदीमन सर का
2 बार क्यों हुआ
2 बार ग्रीन वेलकम हो गया उनको 2 बड़े फोन
नहीं एक जोशी सर का है
हाँ
एक जोशी सर का
को भी दिया था अच्छा
हाँ नहीं ये भी अड्डो तेरी फिक्र नहीं फिर दिया दिमाग पे नहीं पहले एक और ये फिक्र ना कर दो एक और ये है
दोबारा देंगे हम लोग आगे
अच्छा तुसी वो 2 पॉट्स लेकर के थोड़ा दिल घबराई जाता है टेंशन ना लो हाले तक आपको कोई गलती नहीं की, अगे गारंटी कोई नहीं। अपने सारे बंदे देखो, एक सारे बंदे एक बोझ दिमाग पे लेकर चल रहे, वो जेदे दिमाग पे लग गए।
और मैंने वो लिस्ट मैडम आपको प्राइस वाली दे दी थी, वो आपने अनाउंस करनी है ना, वो तो
लास्ट
में है बिल्कुल।
तो अपने सिर्फ पार्टिसिपेट लैब टॉप तक
क्रॉप करा
मटीरियल तैयार किया है, बाकी उन्होंने टॉप से अगला करांगे, बैठ के काम करांगे, पढ़ाई करांगे।
ठीक है। मैम को तो कॉम्प्लीमेंट मिला है सर से।
फिर हमें आवाज पहचानी, कोरिलेट किया।
हाँ कोरिलेट, फिर हमने कोरिलेट किया कि ये तो समन है।
यार सर ने ज्यादा कुड़ी देखा, मैं ऐसे बंगालन आंटी बन के आई हुई है।
सर वहाँ पे एक्चुअली तैयार होके नहीं जाते ना ज्यादा।
एज अ गर्ल एंड एज अ नाउ वी आर आंटीज, यू नो,
यस नॉट आंटी।
दो जवाब नहीं बेबे बन
कोई बात नहीं, हम मत
बेबे बन के भी आंटी।
हम नहीं लगाएंगे आंटी, हम लगाएंगे। वो लगवा दे गली के बच्चे बोल जो मर्जी बोल रहे हैं, मैं फील नहीं करती कि मैं हूं।
जवाब में जेडे फ्रेंड्स हो तो की कहंदे हैं,
अब बोलते तो आंटी है।
हमारी गली में एक लड़का है, मतलब एक कपल रहता है ना, तो ये जो लड़का है कि इन अर्ली 20 में, मतलब 20-21 का तो है ही है, +2 कर रहा था, नहीं कौन सी क्लास का है, इतना बड़ा कैंडल जैसा उसका शरीर है ना, तो वो जब आएगा यार इतना मोटा सा अच्छा लड़का है ना, सारी पहचान दीजिए
आंटी जी। आपने बोला नहीं, बस तेरे भी 2 साल रह गए, उनके 2 साल में तो भी अंकल बचेगा। मेरे को तो आंटी
नेक्स्ट टाइम ना स्टिकर उनकी पेन ड्राइव लगी हुई है। हाँ जी,
ओपन नहीं करके रख दीजिए,
ये बंद करके ये लगी, ये चलेगी।
बस इसका टाइटल ओपन करके रख
ये ओपन है। नेक्स्ट
उनको बता दें।
इससे भी होता है ओपन कर रखते हैं।
हाँ जी, ओपनिंग की
बंद करना होगा।
ठीक है, बंद कर, अपनी साइड से लगा लीजिए।
बंद कर।
उनका बस खत्म हो चुका है, उनका ऑलरेडी। जब टॉप खत्म होगी तो उनको ट्रॉफी दे देंगे, तो अभी आधा घंटा
अनाउंसमेंट टिकट करने से पहले कर दो कि बच्चे ना लिए कभी कुछ कभी गुजर नहीं रहे हैं। ड्यूरिंग द टॉक सेटल डाउन होके नहीं मतलब कि ये जो भी टॉक होगा, ये नेक्स्ट हमारा है लेक्चर, ये कब तक चलेगा? मतलब 12 o'clock तक है, उसके बाद तक है?
12 तो बच्चे जाएंगे।
मेरा मैथ का लेक्चर है, तो मैं बोला कि क्लास में आएगा, फिजिकल भी अटेंड लगेंगे, तो मैं अटेंड कर लूँ कि
Students, kindly settle down in your seat. Kindly settle down, please. We are going to start our technical sessions now.
मैम मैं अटेंड कर सकती हूँ कि अभी मैं वेट कर रहा हूँ?
उसको अपनी रिस्पॉन्सिबिलिटी में देख सकते हो, चलो मैंने ये टॉप करवा करके, अरे हाँ ये टॉप करवा करके फिर आप चले जाओ।
हम बस 3 लेक्चर 11 से 12 में
11 to 12 है, तो फिर बच्चा उधर ना उनसे बात कर लो, नीलू मैम वगैरह से, ये कि मैंने जाना है, तो या जब हर जिस घूम रहा होगा किसी और बच्चे को, मतलब बात कर लो किसी से कि कोई आपका पार्ट प्ले कर देना। ये जो बच्ची ट्रॉफी पकड़ा रही है ना, इसको जाना है 11 से 12।
और ये ना उसको क्या कहते हैं मैम, सर और आ गए हैं, बच्चे बोल दूँ सेटल डाउन
लग जाएगा इधर।
ये लगा कर दिया
नहीं, दूसरे सर की भी टॉक है ना,
तो वो लोड करेंगे ना।
अब उनके पास लैपटॉप है, क्या करें? ये तो
यहाँ पे तो अपना ही लगता है, मतलब पेन ड्राइव में ही देना पड़ेगा उसको, पेन ड्राइव में ले लो।
Students, kindly settle down, please. Volunteers, please help the students settle.
हाँ जी ठीक है। मैम वो बाकी क्लासमेट्स नहीं जा रहे तो मुझे नहीं जाने देते नहीं सब की मुझे सबसे ज़्यादा मैथ ही लगता है मैम मेरे को मतलब 12th तक बायोलॉजी भी था मेरे पास बट आई डोंट नो मैथ और होता होगा मतलब मैथ में डिफिकल्ट नहीं था बट मेरे को ना मैथ में इतना इंटरेस्ट बनता नहीं है फिजिक्स बढ़िया मतलब उसमें स्कोर भी अच्छा था इंटरेस्ट उसमें केमिस्ट्री फिर पढ़नी है तो पढ़ लेते हैं मैथ में बिल्कुल नहीं मन करता पढ़ने का
Volunteers, please help the students settle. Please help them settle. And if there are any students outside the hall, please bring them in. Students are further requested to not move during the lecture.
तो इसी से चलेगा ना ये तो इसी से चलेगा इसको रहने दो बाद में ये डाल हाँ ये रखिए
क्वेश्चनिंग शुरू होगी ना तब किसी वॉलंटियर को बोल देना ओके
Volunteers, please bring the students from outside. There are many students roaming around outside.
नाम क्या है आपका? नंदिनी नंदिनी अभी ना पौना घंटा हो गया है जब हमें थका के रहे हो खुद को क्योंकि टॉक के बाद ही उनको ऑनर करना है ठीक है हमें यू आर टायरिंग दिस योर आराम से बैठ जाओ इधर बैठो उधर बैठो हाँ आराम से बैठ जाओ बच्चा
Settle down, please. Please settle down, students. Volunteers are requested to bring the students in. The students are further requested to not move out of the auditorium during the talk. I welcome all the participants and our esteemed guests to the first technical session for the 5th National Seminar on Recent Advances in Material Sciences. The first talk of the session would be delivered by Professor S.K. Tripathi from Punjab University, Chandigarh, who will be talking about role of semiconductor devices in the society. Before he commences his talk, I would like to take this opportunity to introduce our esteemed speaker to the audience. Professor Tripathi has over 24 years of research experience. He has published more than 200 research papers in various journals of high international and national repute. He has so far guided 21 PhD students, 5 MPhil project students, and 15 MTech students. He is actively involved in research to find out suitable materials for optoelectronic devices. Presently, different types of materials in thin films are prepared in his lab and characterized by different methods. He is involved in synthesis and characterization of a wide variety of materials, such as semiconductor nanocrystalline thin films, oxide materials, dry sensitized solar cells, organic semiconductor thin films, carbon materials, glassy semiconductors, to name a few. We are honored to have a speaker of your caliber with us today, sir. I now invite Professor Tripathi to kindly deliver his talk and enlighten our audience. Professor Tripathi, please.
Okay. So, good morning to all of you, and especially to the organizers, Dr. Sanjeev Kumar and his team. The title of my talk, as has been told by Dr. Shraman, that is the role of semiconductor devices in the society. This I have all of you are knowing this is not the new one. Our daily life is basically that depends upon the semiconductor devices. If these devices were not present, then our life may be certainly in a different way. All of you are knowing that these semiconductors, they are basically the essential component of electronic devices, which are used in different purposes like communication, computing, healthcare, military systems, transportation, clean energy, and other different countless applications. The development in this semiconductor technology during the past 50 years, or you can say more than 50 years, they have have made electronic devices in a very compact size, very fast, and more reliable as compared to the earlier one. Now you can, all of you are knowing, people are talking about the semiconductor chips. These are basically, they have a large number of transistors and other type of devices. And you can say the number of transistors that may be more than the stones which are present in the Great Pyramid in Giza. And today, there are 100 billion integrated circuits in daily life which is used or in use around the world, which is the approximate equal the number of stars in our own corner of the Milky Way galaxy. Nowadays, people are talking, you are seeing that a large number of queue, or you can say the delay in supplying the cars and other automobiles. Very companies are saying 26 months or 30 months or even more than that. And they are giving the cause for that, that is the not sufficient supply of the semiconductor devices and chips or all those things, which shows that the importance of the semiconductor chips and why restoring and increasing their production, that is very, very essential nowadays in the modern living, you can say. So if you, in short, if you put these application of these devices in different sectors and industries which are involved around the tiny bits of hardware, these are computing. All of you are knowing a lot of devices are used in computers, telecommunication purposes, household appliances. Every day you are using it in the houses. Banking, ATM and debit card, also all online transfer of the money, all these things are involved in that business. Security, healthcare, transportation, and manufacturing. So you can say in every day in the daily life, you are using such type of devices. What are semiconductor devices? All of you are knowing, because I have been told by students of BSc, MSc, and research scholars, they will be present. So I have prepared my talk from the beginning, that is from the BSc standard to research. I will move forward in that direction. All of you are knowing that the semiconductors, the materials can be divided into three broad categories. These are conductors, insulators, and in between those two, that is semiconductor. So, and these can be altered by using an induction of an electric field, exposure of light. You can, if you shine the light also, the properties will change, and presence of heat. So these semiconductor materials, these can be divided into two broad categories. Again, one is intrinsic and the other one is extrinsic. Intrinsic means pure and extrinsic means impurity atoms are there. These may be third group or the fifth group depending, and accordingly you will get P-type and N-type materials. And from these P-type, N-type or intrinsic, you can make different devices like diodes and transistors and other ones. If you see, there are different type of materials which are used for fabricating such type of devices. These are germanium, indium gallium arsenide. This is the wavelength sensitivity. Okay, dark current is very high, speed is low, and cost is also low. So I have put several materials like germanium, indium gallium arsenide, lead sulfide, silicon. Silicon, all of you are knowing. Okay, this is a very important material, and no other material is available which can totally replace the silicon. In some of the properties, those are better other materials. But if you say in total, silicon is no replaceable material till today. Gallium phosphide, indium arsenide, antimonite, mercury cadmium telluride. So these are the basically sensitivity is at different wavelengths. Current is also high or low. Speed is also low or high, and so on. So these are the different materials. Many more are also there, but these are the some of the important materials. Now, since we are talking about the silicon, so all of us are knowing that silicon belongs to the fourth group of the periodic table. It has 4 electrons in its outermost orbit. Atomic number is 14 or so. So 2, 8, and 14, that is the number. So you can see here, this is the intrinsic silicon where there is no impurity. The silicon crystal is also there. This is basically in pure monocrystalline silicon, which is used to produce silicon wafers. Okay. In terms of charge conduction, this pure silicon is basically the intrinsic one, and it has low conductivity, or you can say in other words, high resistivity also. And if you want to change its properties, means not only the conductivity, but also from the charge carrier point of view, we are supposed to dope it. Okay. And doping, you know, that can be done by adding the impurities of the third group or the fifth group. Okay. If you dope with the third group, you will get the p-type semiconductor like boron. Okay. Normally boron is used for that purpose, for making the p-type semiconductors. And if you dope with antimony or phosphorus, then you will get the n-type semiconductors. So that is the actual thing by way you can dope these materials, and then you will get the p electrons or holes depending upon the n-type or p-type semiconductors. And if you make the energy band diagram, sorry, lattice constant versus relative energy, you can see different states, 3s, 3p, and 2n state electrons and all those things. This is a band gap. You know, these are the materials, semiconductors are the material which have certain band gap. Now, this picture is showing this is for the intrinsic silicon semiconductor. Here the Fermi level is there. Okay. In case of intrinsic, it is lying at the center. However, in case of extrinsic silicon, the Fermi level either it will be towards the top of the conduction, bottom of the conduction band, or in p-type it will be towards the top of the valence band. So the movement of the Fermi level is basically the doping. So in case of doping, the band areas should not shift. Only the Fermi level should move either towards the valence band or towards the conduction band, depending upon the p-type or n-type. These are the different type of diodes like LEDs, signal diode, IR LEDs, photodiodes, transient voltage suppression diodes, super barrier diodes, different type of Schottky diodes. I will discuss some of the results of this Schottky diodes because in my opinion, this is the easiest type of device which you can fabricate in your laboratory also. These are also known as the metal semiconductor contacts, tunnel diodes, vector. So many different type of diodes are there whose symbols are also present here. Now, then after diode, there is another category that is a transistor, means 3 electrode device, collector, emitter, and base. So this was invented by John Deen in 1948. Okay, around more than 70 years, you can say, and that's why the abbreviation of basically the transference of signal across a resistor. Okay, these are the resistive materials, so that's why. Now these transistors, they have wide applications in all electronic circuits like amplifiers, radio receivers, transmitters. आप लोगों ने पढ़ा भी होगा ग्रेजुएशन में कि कैसे how you can use these transistor as an amplifier or transistor, oscillators or some other device, tank circuit, everything you have studied. This is basically 2 types of transistors are there. One is PNP and the other one is NPN. So this is a circuit which you are making for doing the experiments in the undergraduate laboratory also. So this one, and from there you are finding out the different characteristics. And इसमें ये भी है कि that is a common base, common emitter configurations, and all those things are there. These are the 3 different configurations: common base configuration, common emitter configuration, and common collector configuration. So these are basically, this is a base, this is a emitter, arrow side, and other one is the collector. So 3 electrode system is there. Now the question is, how can you grow the single crystal of silicon? So there are different type of techniques of such type of growth. Basically 2 types are there. One is the crystal growth technique and other one is the epitaxial growth techniques. These 2 types of techniques are used for growing the single crystal of any material. So these are again classified into three different groups. One is a solid process, okay. The other one is liquid solid process, which we are most of the time we are using here, and then the gas solid phase process. So these are, again, we will discuss with this much, that is the liquid solid, that which is most widely used at this much. There are different type of things we are using here. Melt is flux, solution, then hydrothermal and gel and all those things. We will discuss the melt in detail. There are several techniques through which you can grow the crystal, like Choransky, Bridgman, Vanillil, Cryopolis, and float zone. So these are the different main five types of techniques which are used for this purpose. So one is that is the Choransky growth method. MSc students, I think they must have studied are studying this technique, which is basically we have a here silicon dioxide crucible and silicon melt is there. Here the material is going, that should be first melted by heating through the induction or the resistance heating method, and then seed crystal which you are putting here, that is rotated slowly and slowly, okay, and then if you will take it, what will happen? The seed crystal can be withdrawn and you will get the deposition of the silicon crystal. That is one technique. The other technique is Bridgman growth method. This method is basically used for certain semiconductor crystals like 2,5 gallium arsenide, zinc selenide, cadmium sulfide, cadmium telluride, where this process is where it is difficult to prepare from the earlier method, Choransky process. It involves the heating of the polycrystalline material in a container basically above its melting point, and then the slow cooling can be done. That is the process. And few of the physicists, they are growing this type of crystal in their home also, in the kitchen also, home also, just by putting in a melt in a crucible or so. So that can be done using this much. The other is Vanillil method. Here you can see there again it is rotating, this crystal is there. So material is continuously released into the furnace. There is a furnace here where you can increase the temperature, and hydrogen is flown through it, hydrogen and oxygen. At the outlet of the tube, powder is fed into an oxygen hydrogen flame, basically for increasing the temperature also. That is around 2200 degrees centigrade. So what will happen as the powder that will pass through the flame, it will melt into fine droplets which will fall on the supported rod. This is the supported rod also. And a sinter cone is basically formed by the droplet which serves as a sheet for the crystal growth. The next one is the cryopolis method. Here you can see again a heater is there through which you can increase the temperature, and crystals like alkaline halide and all those things, those type of things can be grown here. To initiate the growth, a cooled seed that is from here, that is dipped into the melt, and the furnace temperature that is slowly that is cooled down, okay, due to which what will happen, someone's growth like this allows the crystal to grow in a lower thermal gradient than the Choransky process. So by this way you can grow the single crystal of any material. Next one is the float zone growth method. Many students are familiar with this type of growth, which is basically based on the zone melting principle, okay. Say high purity polycrystalline rod and a non-monocrystalline seed crystal are held face to face here. You can see they are face to face. This is single crystal silicon and this is the polysilicon. You can feed rod is there. With a radio RF heating coil, this you can do. Then what will happen? The seed that is brought from below to make contact with this single crystal, you can see molten zone, and due to which what will happen? The drop of the melt that will form at the tip of the poly rod. What will happen due to that? As the molten zone is moved along the polysilicon rod, the molten silicon solidifies into the single crystal, and simultaneously the material can also be purified. So these are the techniques which are coming under the crystal growth. Then the next one is the epitaxy growth. Basically, epitaxy, you can see such type of substrate wafers and epitaxial layers are there. Okay, So this refers to the deposition of a crystalline overlayer on a crystalline surface. So on a crystalline surface, you can deposit with the help of epitaxial growth technique. And this word epitaxy, that is basically coming out from the Greek word that is for the surface and the axis, and which relates to the atomic growth of a substance onto the surface of the substrate. Here, you must ensure the atoms should be aligned with the crystal lattice where you are depositing such type of material. It is a form of atomic engineering, or nowadays people are talking about the nanotechnology and all those things. So that is the actual thing in the epitaxy. There are two types of epitaxy methods are there. One is the homoepitaxy and the other one is the heteroepitaxy. So homoepitaxy means the film and the substrate are of the same material that you can do. Suppose you want to deposit on a silicon surface, then silicon film can be deposited on that one. That's why homo word is here. Often used in silicon and silicon growth, and this grown layer, they are purer, okay, than the substrate and can be doped independently of it. That can be done with. Similarly, in heteroepitaxy, the film and the substrate, hetero word is there, so certainly substrate material and the film material, that will be different. Like if you want to deposit aluminum arsenide or gallium arsenide, so that type of film can be deposited using a different technique, and that is known as the heteroepitaxy. Here, through this, that allows for optoelectronic structures and band gap engineering devices. Normally, engineers, all of you are knowing, engineers are making the structures of the material. So that's why engineering word I am using at different times. Now, these are the different techniques, which includes solid phase epitaxy, liquid phase epitaxy, metal organic vapor phase epitaxy, and molecular beam epitaxy. These are the four main techniques through which you can deposit the thin films of different. Now, solid phase epitaxy, basically, it is a transition between the amorphous to crystalline phases of the material. All of you are knowing what are amorphous materials, what are crystalline materials. From the structure point of view, you can divide your material into three broad categories. One is the crystalline, amorphous, that is non-crystalline, and the polycrystalline. So that type of thing. Usually it is done by first depositing a film of amorphous material on a crystalline substrate, and then the substrate where you have deposited, that should be heated at above the room temperature. Okay. Then what will happen? With time and with temperature, the structure of the amorphous material, that will change into the crystalline one. And that's why we are saying this is a phase transition is taking place. The advantage of this technique is this offers flexibility of creating multiple layers, okay, compatible with current processing environment, and it is useful for a stack SRAM and EEPROM cells. Those are available here. The next one is the liquid phase epitaxy. It is basically a method to grow semiconductor crystal layers from the melt and the solid substrate. This happens at temperatures well below the melting point of the deposited semiconductor. That this picture is, you can see how this material can be deposited. The semiconductor that is dissolved in the melt with another material, and at conditions which are close to the equilibrium between the dissolution and deposition, the deposition of the semiconductor crystal on the substrate is relatively fast and uniform. That is one. Advantage of this technique is it is near equilibrium growth, excellent crystal quality you can obtain, inexpensive because cost factor is very, very important whenever you are making synthesizing any material or making any device, and widely used for LEDs and laser diodes. There are some difficulties are also, that is difficult to scale up for production of excellent crystal quality. Dimensional control is poor as compared to the earlier one, and structural complexity that is limited in this one. The next technique is the MOVP technique, that is metal organic vapor phase epitaxy, or normally we are using the word MOCVD, that is metal organic chemical vapor deposition technique. This is used for growing high crystal single crystalline form of different materials on different type of substrates. Okay, this is used for growing the materials like aluminum gallium arsenide or gallium arsenide gallium indium phosphide or gallium arsenide, and so on for the optoelectronic, photovoltaic, and high-speed electronic applications. The advantage of this technique is basically this is conceptually simple as compared to the other one, and used for some gallium arsenide epitaxy where high purity, that is low background doping, that is needed. This disadvantage of this one is we are using the toxic gases arsine, phosphine. These are very, very poisonous. Even few ppm is sufficient to take you from this world to the another world. So one should be very, very careful whenever we are tackling such type of gases. I can give you one example. In Delhi University, people have purchased such type of gases, and they have never opened the valve of those cylinders. So when I have applied a project in the DST, they have given me an offer that you can take those gases from there. So this is a very, very complex. People are purchasing in the universities or institutes, but one should be very, very careful. One incident of such type of gas, which is even lesser toxic than these gases, that is in Bhopal gas tragedy. All of you are knowing. So that is a major disadvantage of this type. That is another one is the molecular beam epitaxy in solid source MBE. Elements such as gallium and arsenic in ultra pure form, which are heated in separate quasi-Coulson fusion cells until they begin to slowly sublime with each other. The gaseous elements then condense on the wafer, where they may react with each other. The term beam means that evaporated atoms do not interact with each other or vacuum chamber gases until they reach the wafer due to long mean repose of the atoms. And techniques like RHEED, these are used for monitoring the growth of the crystal layers. Advantage of this technique is this is extremely flexible, very low defect concentration. Okay, because defect, all of you are knowing in material science, that is very, very important parameter to find out how the distribution in the inside the energy band gap and all those things that is there. Layer by layer growth allows for novel architectures, artificial heterostructure, quantum wells, those can be prepared using this technique. And this is primarily used for the semiconductor research. Again, the same type of disadvantages there, like toxic gases and all those things, low deposition rate, and all these things are there. Then chip, after that, silicon chip. I have already told you large number of devices are present there. So basically this is a pattern of interconnected switches and gates on the surface of a crystal of semiconductors. Normally we are these switches and gates which are present in the silicon in the chip, that is basically areas of N-type silicon, areas of P-type silicon, areas of insulators, lines of conductors basically which are used for the interconnecting different joining, and normally for that purpose we are using aluminum, copper, titanium, all these things. The connection from the chip to the outside world are made around the edge of the chip to facilitate connections to other devices. That is here. So there are different fabrication technologies. Okay, so we are using for that purpose wafers. And these wafers are prepared from the silicon crystal, which you are growing from different techniques, which I have already discussed. And these vary of different diameters. Normally, currently we are using 150 millimeter diameter, 200 millimeter diameter, and 300 millimeter diameter. And thickness of these wafers is less than 1 millimeter or so. Okay. Then surface is polished to optical smoothness. Optical smoothness means of the order of nanometer or so. Optical visible portion, all of you are knowing, that is 400 to 700. So उस range पे हमें इसमें smoothness चाहिए. And then this wafer is ready for the processing, and each wafer will yield many chips, and chip die size that varies about 5 millimeter by 5 millimeter to 15 millimeter by 15 millimeter area. So, and the whole wafer is processed at a single time. Okay, that can be done. There are different techniques, fabrication process. I will not go into the detail because time is limited, but certainly these are the different techniques which are used for the fabrication of such type of devices. That is wafer crossing, I have already told you, different. Then substrate cleaning, that is very, very important parameter. Otherwise, what will happen? The dust particles or fingerprints or some other type of things may be present there. For that, you need a clean room. I will discuss later on. Oxidation process, oxide layer should be deposited either by dry oxidation or wet oxidation, depending upon the condition. Lithography, different type of lithography techniques are there. Optical lithography, electron beam lithography, laser lithography, or you can say X-ray lithography, ion beam lithography, different type of lithography techniques are there. Doping, or you can say impurity addition for making N-type and P-type. Okay. Again, the doping is that can be done either by diffusion or by ion implantation using the ion implanters which are available. Then etching. Etching means to remove unwanted thing. जो चीजें आपको जरूरी नहीं है उनको आपको निकाल के बाहर फेंकना पड़ेगा. जैसे घरों में हम लोग जब सामान हमें जरूरत नहीं होती तो निकाल के फेंक देते हैं. But here in chemically we are doing this process. Every day we are washing our hands in the morning. So that is also a etching process. For that purpose, sometimes we are using the water and along with the soap and some other chemical agents also. So etching means to remove unwanted things which you do not need. Then metallization, because once the device is formed, then you need to take the contacts. And for making the contacts, this must be checked whether you are supposed to choose a metal which should make ohmic contact with the semiconductor device. Ohmic and non-ohmic contact, two types are there. So ohmic contact must be there. Otherwise, that will make another device. Okay, which I will discuss you. Then after metallization, then packaging is there. And after that, the testing is, after metallization, testing is there. Whether your device is giving the proper characteristics which you need for that purpose. And after that, assembly and packaging, and then marketing, that is the last step, which is do it. So these are the steps which are used. Normally the cleaning is done by the RCA method, which is Radio Corporation of America Clean. It is a standard set of wafer cleaning steps, which need to be performed before high temperature processing steps like oxidation, diffusion, metallization, or other things. It involves the following chemical process, that is the removal of organic contaminants, that is organic clean plus particle clean, then removal of thin oxide layer, okay, then removal of ionic contamination. Removal of ionic thin oxide layer means silicon is a native, silicon is making native oxide layer when it is present in the environment. Oxygen is present there, so the silicon dioxide layer is there. So before doing all those things, you must first clean the substrate, wafer you can say, and after that you must remove the silicon dioxide layer which is present on that particular wafer or board. Then removal of ionic contamination, that should be done by the ionic cleaning. And fourth step is rinsing in deionized water, okay, and then drying. Deionized water, most of you are knowing, basically no ion. Normally we are saying water is non-conducting, but tap water is conducting because metal impurities or minerals are there. So those should be removed. Okay, that can be done with this much. Then need for the clean room. Why do you require a clean room? So all of you are knowing in this room a large number of dust particles are there whose size is less than the resolution power of your eyes, and due to which you are not in a position to see. Okay, and कई बार आपने देखा होगा जब घरों में झरोखे होते हैं, लाइट आ रही होती है तो उसमें डस्ट पार्टिकल आपको नजर आ रहे हैं. उसमें देखें तो नजर आएंगे, अगर दूसरी जगह देखेंगे तो नहीं आएंगे. Okay, but maybe even less than that also size is also available. So for that purpose you need a clean room, means very less number of dust particles. Ideally तो आप zero तो कर नहीं सकते, you cannot do like that, but that number should be very, very small. Okay, so this is basically for the IC fabrication facility. It requires a clean processing room, especially in the area used for lithography. अगर आप लोग कभी जाना चाहें, डॉक्टर संजीव से सभी से है, आप यहाँ पे STL मोहाली में है, Semiconductor Complex Limited. Mohali is very near from here. You can go and see there. So that type of things are there. The need for such a clean room arises because dust particles in the air that can settle on a semiconductor wafer. They can sit on here. And if you will deposit a film on that, there may be a large number of holes. Pinholes are there. And due to which what will happen, let us suppose you have made a layer by layer deposition, P-type layer, then I-type layer, and then N-type layer, which is known as thin film technology. And if you will make a contact from the bottom as well as from the top, what will happen? If the pinholes are there, then there may be possibility that the metal atoms, they will go from one side to another side, and they will shorten the device. So that when dust particles adhere to the surface of a photomask, they behave as opaque patterns like this. Okay, and on the mask, and these patterns will be transferred to the underlying layer along with the circuit patterns. This you can see. So that's why you need a clean room environment. Now, how can you prepare the thin films? I will show you some of the results also from here, which I have made here. So this is a film. This is a film which we have deposited on a glass slide. But for the electrical measurements, we are depositing the film on the Corning 7059. Because this film, these are the resistive materials. So they are making a resistance here, and a parallel resistance of the substrate is also there. So there is a parallel combination. So what will happen? If you will connect with the battery, the electron will flow from the lower resistance side as compared to the higher one. So one must have the resistance of this glass substrate higher, much more higher as compared to the resistance of the film. This Corning 7059 glass, Corning is the name of the Corning door company. Most of you have heard the name. This is a US-based company, and 7059, that is the number of particular glass which is alkali-free glass. Its resistance is very high, and these are this material. These films have been used before deposition of these films. 2 electrodes have been deposited, which we are using as the indium metal, because you know these metal contacts, they have a natural tendency to diffuse inside the semiconducting material, even at room temperature also. With the time they will diffuse, and if you will increase the temperature, certainly the rate of diffusion that will increase. So we are supposed to choose such a metal which should not go inside the semiconducting materials. Ideal is gold. Ideal is gold, but you know gold is very costly. So we are choosing this indium metal. We have done the experiment by taking several metals, and then we have find out how the diffusion rate can be obtained. And there we have seen aluminum has the silver has the maximum diffusion inside the semiconductor, which we are studying the material, and indium has the minimum one. So that's why we have chosen the indium, number one. And number two, when we have taken the IV characteristics, they are giving the ohmic content. That is the 2 conditions must be taken whenever you are choosing any metal electrode. This is a basically cadmium selenide thin film, which we have deposited using the physical vapor deposition technique in our laboratory. And this is a transmission electron microscope TM picture, which I have taken from our university. Then you can see here, these are some of the X-ray spectrograph of this material. This film has been deposited at 3 different pressures. Means for that purpose, we have chosen the argon gas, because argon gas is not interacting with the cadmium selenide material. Okay, so for that purpose, we have made a device through which a very fine gas flow that can be done towards the substrate, directly towards the substrate. Then 3 different pressures, at 3 different pressures, we have deposited this film at -5, -2, and -1. And then we have seen, we have taken the X-ray spectrograph, and here from this picture, when we have calculated the particle crystallite size, that is around, it varies from 4 nanometer to 60 nanometer. Okay, just by changing the pressure. And that's why sometimes we are saying this is a band gap engineering. because if you change the particle size, means you are also changing the band gap of that material. Okay, material is same, only the condition is slightly different. Okay, so that's why it is known as band gap. Band gap engineering. At this pressure, means -5 millibar, the particle crystallite size was around 4 nanometer. However, at this it was around 16 nanometer or so. So that we have obtained. Then we have done the different experiment, because whenever you are synthesizing the material or preparing the material, even in the kitchen also, whenever you are cooking the food, the first thing is to, before serving to anyone, you are taking that food in a spoon and putting it into your cup. Just taking, whether it is salty, everything is fine or not. Even रामायण में एक प्रसंग भी आता है कि सबरी ने जब राम जी को बेर खिलाए तो पहले उन्होंने टेस्ट किया, है ना, तो उसमें भी आता है। तो योर टंग, बेसिकली जो आपकी जीभ है, दैट इज एक्टिंग लाइक ए डिटेक्टर और कैरेक्टराइजिंग टूल। सो दैट्स व्हाई few experiments are required to obtain that what type of material you have prepared in your laboratory, whether this is good for a particular application or not. So I have just, I will not go too many experiments, only few experiments I will discuss. The one thing is the mobility and relaxation time basically. So all of you are knowing that this electron conductivity, the photocurrent, that can be expressed like this expression. Okay, E is nothing, basically this is the electron charge, L is the length of the electrode, okay, V is the voltage which you are applying, and S basically that is the distance between the two electrodes which you are taking, and B is the thickness, and V1 is the electron mobility. Okay, so from here the concentration of photoexcited electrons, that can be written as N equal to G, which is known as the free electron generation rate, or you can say rate per unit volume, and tau. Okay, so from here again this G you can write as alpha into this much, alpha is the Johnson coefficient, and all those expressions are there. And finally you can get the mu tau, because these are the function of lambda. Mu tau, that is given by photocurrent, F D upon ELV into G. That is, from here one can calculate the drift length. Okay, so for that purpose we have taken this setup, which we have designed and fabricated according to our own requirement in the laboratory. Okay, so here basically this is a cryostat of stainless steel. You need a metallic chamber because lot of electromagnetic radiations are there, so they should not interact or they should not affect the actual current of that particular material. We are shielding with a electromagnetic shielding, can be done with the help of the metal. Okay, and this is a copper rod which is inserted in this liquid nitrogen. It is a vacuum shield. So with the liquid nitrogen you can go below the room temperature. Okay, and if you want to go above room temperature, this is a heater also. So you can heat also and make a particular equilibrium temperature also. These are the two windows, glass windows are there. From one side you can shine the light. Okay, single wavelength monochromator used for that purpose, and the other side you can have a spectrophotometer through which you can, a detector is there, you can monitor the thing. Number one. Number two, the beauty of this setup is that what normally people are doing, they are doing the electrical measurement in one setup and optical measurements in other setup, and they are comparing with each other. Then in that case, because the experimental conditions are different, so it is difficult to understand. Sometimes you are getting a lot of difference in it always. So the simultaneous measurements can be done. Electrical measurement can also be done. So for that purpose, this sample is here. Okay, and this is connected with a cable lead here, and two instruments. One is for the voltage, KAUSHAL 224, which we are using for that purpose, and for measuring the current and other parameters, KAUSHAL 65178, that we are using for that purpose here. So these are some of the spectra which we have obtained, that is photocurrent versus photon energy at different biasing voltage and all those things. And from here we have calculated using those earlier formulas, mu tau product and that can be drawn here. Now here from there, one can calculate this much also, this parameter LV and versus photon energy. And from here we have calculated the different parameters, okay, which are I have kept here. And we have seen the copper effect also, how the copper is affecting the property of this cadmium material. For that, we have taken the different concentrations, but this result is for 1% copper is there. So here you can see that the photosensitivity that increases 10 times or so, and this mu tau product is also around 100 times, and this increases from 3.4 to diffusion length to 22. So this is because this is due to the increase in the lifetime of the electrons, due to which what will happen, the decrease of the capture cross-section of the electron has taken place, which is confirmed by the time of flight experiment also. This much. So this is the time of flight experiment, which we have again designed for our own requirement. The basic principle is for that purpose we have used the pulse laser 1064 nanometer. The pulse width is 10 nanosecond also. Okay, and we have deposited a aluminum semi-transparent electrode, and this is the thickness of that one. And the bottom is also aluminum electrode, and DC source power is applied. And then storage oscilloscope we have in our laboratory. So on that we have recorded the data. So this is the spectra which we are getting here, and we can see that the increase in the mu tau product, which can be told that this is in good agreement with the earlier experiment also. A small discrepancy we are observing in the time of flight experiment, because that is because the wavelength which we are using for this purpose, because that was the only available laser in our laboratory. So that is a small discrepancy we are using. Okay, and because low penetration depth of the laser is there, this is absorbed at the surface of the thin films. Increase in the surface recombination that is taking place, and increase in recombination rate of photogenerated electrons with holes that is taking place. The next experiment which we have performed, that is a thermally stimulated current. Which I have. So next experiment is a thermally stimulated current, which we have performed in our experiment. Again, the same sample holder we have used for that purpose. In this experiment, what we are doing, we are going from above room temperature to lower temperature, okay, and measuring the dark current. We reach at the lowest temperature, that is around liquid nitrogen temperature or so. Shine light for few minutes. Here it is around 20 minutes or so. Then switch off the light, wait for 30 minutes so that the system can get stabilized, and after that we start heating. Okay, and then we are seeing how much difference in the dark current we are getting. And this difference is basically the charge carriers which you have generated after shining the light. They are trapped inside the defect states. So that type of mechanism or study we are doing with the help of this experiment. That's why it is known as thermally stimulated current. There are two methods are there for analyzing this data. One is the different heating rate method using distillation, and the other one is the Gaussian fit method. We have used both these methods for calculating. And here you can get, we have obtained such type of spectra. And from here we can calculate, we have calculated the trap depth energy. Heating is trap depth energy. That comes out to be 0.68 electron volts or so. So this much, this is other one at different heating rates we have done. And then this is from the Gaussian fit method, from where we have calculated this capture cross section and all those things we have obtained from this. So here you can say the activation energy which are small as compared with those of the recombination centers in the thin films which are present. All of us are knowing recombination centers are there, as well as the trapping centers are also there. Trap energy level in doped bismuth thin films are closer to the conduction band, which we have seen also, 0.68 electron volts or so. The trapped electrons can easily escape to the conduction band. Shallow trap level originates from doped impurities, and trap density are higher than the concentration cause defects in the crystalline CDFE, which is basically due to the decrease of the nanocrystalline growing size, which I have already seen from 16 nanometer to 4 nanometer or so. Fracture cross-section or trace are low, which gives the strong repulsive barrier to fracture carrier, and fracture cross-section decreases after the addition of copper, which shows an improvement in the transport properties of the thin films. So I think time is less, so I will skip some of the parts, and then a device, simplest device, which I would like to discuss in 2-3 minutes. This is basically metal semiconductor contact. All of you are knowing that the metal is deposited on a semiconductor, and here it is not making the ohmic behavior. Okay, it is making a non-ohmic behavior. So it is making basically a device junction type of diode, and that's why that is also known as Schottky diode also. So आप लोगों ने MSc student, they must have studied in their classes. So I will go quickly. I will not go. This IV characteristics which I have drawn, that can be calculated with the Schottky barrier diode. Here I is the current which is flowing, IS is the saturation current density, N is the identity factor, Richardson constant, absolute temperature, Schottky barrier height, and Goldman constant. ये SMG की book में सारा दिया हुआ है. Okay, so I will not go into the detail of this much. I will similarly the CV characteristic, current voltage characteristic, that also you can study this much. For that purpose, we have made the we have deposited this cadmium selenide film on a ITO, indium tin oxide substrate. This is through basically this is a transparent substrate, but one side is conductive. So for taking the contacts and all those things. Other side we have deposited the gold junctions, and then from these equations one can calculate the carrier concentration and VN, then depletion layer width, all these things. Again, these are the equations which are there in the SNG book. So I will not go into the detail of this much. This is the result. This is basically IV characteristics which we have done. We have measured from 303 Kelvin to 333 Kelvin. We have gone up to that. We could not go above that temperature because the phase transition is taking place in that particular material. So I could not go this much. Then we have plotted a Richardson plot. Okay, here you can see here. After that, barrier height from the IV characteristics, we have calculated this barrier height, which comes out to be around 0.485 electron volt at room temperature. We have done simulation also, and here you can see a very perfect alignment is there. Then we have plotted the barrier height versus identity factor. Okay, and from here one can see that the graph between the barrier height and the identity factor in the major temperature range 280 to 300 Kelvin. It's clear that these two values are correlated linearly with each other. Okay, and we justify the lateral inhomogeneity in the Schottky barrier area also. Then from the CV measurements, we have plotted 1/c² versus voltage here. And from here, we have calculated the parameter, that is the carrier concentration, which comes out to be around 10 to the power 17 or so. And the value of the glacial layer weight, that is around 10 to the power minus 4 centimeter multiplied by 6.87 or so. So here we have obtained, we can see here, that is from the curve 1/c² versus voltage, that will give the BH values, barrier height values, which are higher, which we have measured from the IV characteristics. Why it is so? That is a question. So the difference between the measured IV and CV Schottky barrier height in the metal semiconductor barrier is also evident for the Schottky barrier height inhomogeneity is there. The discrepancy between these two values is that in case of CV, okay, that is dominated by the current which flows through the region of the low Schottky barrier height. However, this is in case of IV. However, in CV, the barrier height is influenced by the distribution of charge at the depletion region boundary, and at this charge distribution, which follow the weighted arithmetic average of the Schottky barrier height inhomogeneities. So this is all about.
Thank you so much, Tripathi sir, for such a knowledgeable talk. The session is now open for question and answers. Students can raise their hand if they have any questions. There's one question by a student.
We see that China, Taiwan, Singapore, South Korea, Japan, these countries are located in a similar region, but they are far outperforming us when it comes to making of these chips. According to recent data, India is spending more money on importing semiconductor chips than we are spending on oil. So, considering that we are trying to create an environment for entrepreneurs, for startups, and the new world is all about computers and technology. So, if we, so what do you think are the challenges in establishing a strong chip manufacturing market? Or basically the issues are with what I'd say paper fabrication only, because we have done very well in electronic design and other places, but with fabrication we are not able to establish our facilities. So what do you think are the challenges, and how you feel the policymakers and the researchers alike should overcome?
Yes, the most part of your question is very nearby. You have semiconductor complex in India. At least it has been made. Government of India has decided to establish a center where the such type of devices and all those things. If I am correct, at that time more than 600 crore has been spent for establishing that. And at that time 600 crore was very big value. Nowadays it is not so much. But you know, in our country, I am also the citizen of that country. Whenever you are getting a government job, we are saying that we have got the pension from the beginning. हम लोग काम करने के लिए तैयार नहीं हैं, and blaming to others, and due to which what will happen, that has become the elephant, white elephant. That is the one part. Now again, the question you have put in the other part of the question, what are the challenges and why? Now the government of India has made a policy to fabricate such type of devices or chips in our country. But you know, in one day it is not possible. Certainly it will take few years. And different companies which are fabricating such type of devices in China, Taiwan, and all those things you are saying, they are trying to come in our country. But our labor laws and other policies are so much that they are afraid that if they will come here again, maybe some other government will come and they will again start the same thing. But certainly, no doubt, government of India is spending a lot of money to promote such type of companies. I was reading in a newspaper around $60 Arab. Government of India is subsidizing to foreign countries like Apple and all those things. The policy बन रही है, and surely the situation will improve, no doubt for that. But एक दिन में आप चाहेंगे ऐसा हो जाए, क्योंकि companies तो आ जाएंगी, from where the workers will come. trained people will come. वो तो हमें ही provide करने पड़ेंगे. So that is a process, and hope for the best. Government of India has started. The last budget also they have kept a lot of money for that purpose. So चीजें improve होगी ऐसा कुछ नहीं.
Another thing that I read about, there were two companies that were ready to invest and set up plants. One was they were going to set up in Gujarat, and another one it had backing from IBM. But due to legislative issues, failed. So these things have been going on for many years, but I think it's the institutional issues that are putting us behind more than.
These are the policies which the government of India is doing, taking the right. That's why hope for the best, I can say. And certainly ours is a democratic country. So every citizen has also the right. So if there is any discrepancy, with time and time, government are removing such hurdles and all.
Any more questions from the student? Okay, if there are no more questions, let's thank the speaker once again for such an interesting talk. I would now request Dr. Deen to find the mini token of honor to our esteemed guest. Students, kindly be seated.
अभी ऑफ कर दो, बाद में ऑन कर लेते हैं. चलो
After such an interesting talk by Dr. Tripathi, now we have our next speaker with us, Professor Ravi Kumar from NIT Hamirpur, who would be talking about nanotechnology for application in electronics, P-type transparent conducting oxide. Professor Ravi Kumar is associated with the Department of Material Science and Engineering, NIT Hamirpur. He obtained his MSc Honours degree from GNDU Amritsar and his doctoral degree from Tata Institute of Fundamental Research, TIFR, Mumbai in the year 1994. Professor Ravi Kumar has a wide administrative experience. He has acted as a group in charge Material Science IUAC New Delhi during the years 1996 to 2009. Head Center of Material Science and Engineering, NIT Hamirpur during the years 2009 to 12 and again 2016 to 19. Principal, Dayal College of Engineering and Technology, Upgradation during the years 2013 to 16. EC member, Central University of Himachal Pradesh during the years 2017 to 2019. He also has a wide research experience. So far, he has guided 22 students for their PhD degree and 4 are their ongoing students. He has published around 338 research papers in various peer-reviewed journals. He has written 9 articles in edited books and also delivered over 150 invited talks in various international and national conferences as well as symposia. His research profile boasts of an H index of 41 and I-10 index of 220, which is extremely commendable. His area of specialization is functional oxide materials. We are truly honored to have you with us, sir. I now invite Professor Ravi Kumar to kindly come up the dais and address the audience. Another request to the students to kindly listen to the talk carefully. You are really going to benefit out of it, so please be seated.
Good noon to everyone. First of all, I am very thankful to the organizers, especially Dr. Sanjeev, who has given me an opportunity to discuss our recent ideas with the young minds so we can get a better feedback to improve our research. I am very thankful to Dr. Tripathi that he has built up the background for my talk, and so I can start from the beginning. Where he left, I can start from that. So basically today, I am talking about the transparent conducting oxide materials. These are two phenomena of opposite direction. The material should be transparent. It means that the visible light can pass through that. And the material should be conducting so we can pass a current through that. And if we want to pass a current, we require some density of states. The density of states will object the transparency of light. Because all the insulators are transparent. Your glass is transparent because they have wide band gap. And if you require the conduction, you have to engineer the band gap or introduce the density of states in between the band gap. So the conduction will be possible. So we are going beyond the nature, which has given me a transparent material, which has given me a semiconductor material or metals or conductors which can conduct. So we physicists उल्टी खोपड़ी के होते हैं. हम हमेशा वो चीज सोचते हैं जो सीधी सीधी नहीं है. So that's what is a transparent conducting material. So this is the background of that. Why we need transparent conducting? Where I can change my slide.
So you can change it from the mouse. Mouse, just by clicking.
From this.
This side you can click.
Okay. So the transparent conducting oxides. I think my pitch is very high. I don't need this mic. So the transparent conducting oxides have become leading candidate for invisible electronics. मिस्टर इंडिया पिक्चर तो देखा होगा आप लोगों ने, ज्यादातर पैदा होने से पहले रिलीज हुआ है. There was an invisible man. That was some fiction. Now we physicists want the real sense of the fiction. So we want to have some invisible electronics as they exhibit high transparency and high conductivity in a single material. So we want, being a material engineer, being a physicist, condensed matter physics, we have to address this question. Now, sometimes we say we are doing some new research. It is not that. The time is an important time. When it comes into the realization, then that research definitely develops. This first report of transparent conducting thin film of cadmium oxide was published by Bedecker. Bedecker is again an Indian. बहुत सारे लोग बोलते हैं ना वेस्ट से, जैसे डॉक्टर साहब बोल रहे थे कि भैया भारत में सारी साइंस डेवलप होती है। बेडेकर ने 1907 में, in 1907, he has given the concept that the material of cadmium oxide is a transparent as well as we can make it conducting. So transparent conducting oxide is 2000, last century, first decade was there. But at that time, no electronics was developed, nobody was bothering, his research was suppressed. And now in a modern era, in the last decade of the 20th century, people realize that now we have a very nice transistor. Deen has developed the transistors when our country was getting freedom in the same time, and the same Deen got that superconductivity theory also, BCS. The BCS B was the same Deen. So those people were doing many work. Then we have developed the electronics, all the devices, semiconductor materials. And as the development of science and technology is occurring, तो जो पेप्सी वाले ऐड देते हैं ना, दिल मांगे मोर. So the same philosophy is in the science also. We also are very crazy to get better and better devices of the material. That was the transparent conducting oxide material again picked up the things and the idea of invisible electronics for the security circuits. So many materials were developed which were transparent and conductor. Like ITO, my previous colleague Dr. Tripathi has told you, indium tin oxide glasses. Then all these galaxy of materials people worked. All these materials are of N type. And there was a hardly available P type transparent conductor. So basically my background was from magnetism. I was trained by ex-vice chancellor of Punjab University, Professor Grover. I am his first student. So he trained me as a magnetism person. Then I developed from superconductivity to the magnetism. Then after completing my administrative job as a principal director of Punjab Government Engineering Institution, when I went back, I thought I should do something special. So this is my advice to all the scientists or the physicists. Please, after 5-6 years, to switch over your area of research, then you will be more productive than if you continue in the same thing. किसी न किसी दिन तक दिमाग सैचुरेट हो जाता है. तो जब आप दुकान बदलते हो तो माल भी नया आता है. That is the philosophy I am working on. So I thought I should work on the P-type semiconductor transparent conducting. So why we want to do a transparent conducting oxide? There are many applications. The flat panel display in behind you, there is light there. LCDs, LEDs, solar cells, invisible security circuits, smart window, touch screen. हम सब लोग इसका इस्तेमाल कर रहे हैं. कुछ चीजों का कर रहे हैं, कुछ चीजों का नहीं कर रहे. Where we are not using, there is an incapability of the material or non-availability of those materials. So that is the basic circuitry, how we can apply that. Then P-type transparent conducting oxide, not a trivial task. The title we have given because as compared to the N-type TCO, P-type oxides are generally less conductive and less transparent. I will tell you why. बहुत simple science है उसकी, कोई बड़ी rocket science नहीं. Basically, it depends on the band structure. The nature of the band structure limits the potential of most common oxides. Why? The oxygen 2p orbitals are having a localized of the valence band, and those bands are very flat. अब देखिए फ्लैट बैंड की बात तो वैलेंस बैंड इज वेरी फ्लैट. आपने बीएससी में एमएससी बिकॉज ऑल आई हैव सीन यंग स्टूडेंट्स हु हैव रिसेंटली स्टडीड, मेरे तो बहुत साल हो गए वो पढ़े हुए. We say there is a conduction band. EK diagram आप लोगों ने सभी ने पढ़ी. There is a conduction band and there is a conduction band and there is a valence band. And then we say heavy electron and heavy hole. सुना होगा mass of the effective mass of the hole and effective mass of the electron. Now, if your band is flat, if you take the EK diagram and make the relation with the mass of that, if more is a flatter the band, whether it's a conduction or it's a valence band, the mass of effective mass of the hole will be very high. When the effective mass, because the hole will be localized around the oxygen 2p orbital. Now, that hole, heavy hole, will not move. Effectively, it cannot freely move from one side to another side. So the conduction will be less. And if that flat band will come, the transparency will also be blocked due to the oxygen localized 2p orbitals. Now, if a positive hole is introduced by substitutional doping, that may localize on a single oxygen atom, which will not allow to drift it within the crystal lattice. हम लोगों के दिमाग में बड़ी एक कंफ्यूजन रहती है कि क्योंकि हमें क्लासरूम में किताबों में ये पढ़ाया जाता है कि हम सोचते हैं कि ये बैंड है, ये कंडक्शन वैलेंस बैंड है, ये कंडक्शन बैंड है, जहां ये जा रहा है वो हम सोचते हैं कि सारी दुनिया ऐसी है जैसे हम एक डायग्राम बनाते हैं. In fact, it is not like that. Basically, you have the crystal structure, you have a lattice site, the electron and the nucleus, and how they will be forming the band structure, and that is the energy levels we are talking. So basically, the conduction of the hole or electron is the motion of the hole in the lattice structure. Okay? समझ लगी ना? देखिए मजा तभी आता है जब आप लोगों का रिस्पॉन्स मिलता है. So if you realize that that kind of motion is possible, so but what is happening if you can dope some hole and it will be trapped in the localized oxide orbitals, 2p orbital, and it will not allow. अब आप लोग इस कमरे में हैं, दरवाजा बंद है. It means you are localized in this room. अब तुम में से कोई भागना भी चाहे तो पहले दरवाजा हिलाएगा, बाहर बंदा खड़ा है, आपको नहीं जाना. Same way, the oxygen is playing a role as a चौकीदार, not allow the hole to be moved away. अब इसको मूव कराना है हमें. अब हमारी समस्या यह है कि हमें पी टाइप बनाने ही बनाने हैं. अब इसको मूव कराने के लिए कोई ना कोई फिलॉसफी ढूंढनी पड़ेगी. So basically, what is that? What?
मैडम जरा इधर देखिए, कुछ हो गया है यहाँ.
Okay. Now, what is the origin of P-type transparent conductor? And how we can make? There was a scientist, Japanese scientist, Sato, in 1993. He was the person who converted the nickel oxide, which is anti-ferromagnetic insulator, into the P-type transparent semiconductor. But their transparency was very less, around 20%, and their whole conduction is there. That was the leading point. When you start a research, you start digging कि किसी ने कुछ किया हो कि नहीं किया, कुछ तो रास्ता मिले ये आइडिया को परस्यू करने के लिए. Then there was we got कि in 1993 तो सैटो भाई साहब थे जिन्होंने ये प्रयास शुरू किया, लेकिन उनका फेलियर हुआ. फेलियर इज ऑल्सो गुड इन रिसर्च. ये मत सोचिए कि मेरा आइडिया शुरू किया है वो सक्सेसफुल नहीं हुआ. It will lead somebody else to think about that. So after that, lot many years were happened and nothing was coming. लोगों ने सोचा, हमने भी सोचा कि वो क्यों नहीं रहा. जब ये चीजें नहीं होती हैं तो कुछ ना कुछ रीजन होगा. So then the solution for p-type conductivity is to modify the valence band edge. How we can modify the valence band edge? By basically there the chemistry comes in. कई बार लोग मैं फिजिसिस्ट हूँ, ये केमिस्ट है, आपस में लड़ते झगड़ते रहते. कोई कहता मैं मैथमेटिक्स मैं बढ़िया आदमी हूँ, है ना, ये मुझे ज्यादा क्वेश्चन लिखनी आती हैं. और हमारे समाज में जिसको ज्यादा मैथमेटिक्स आता हो, जिसको ज्यादा अंग्रेजी आती हो, उसकी हम बहुत इज्जत करते हैं. लेकिन फिजिशियंस बोलते हैं कि भैया हम किसी से कम नहीं, हमारा भी जमाना है, हम तो रियल लोगों को फिजिकल वर्ल्ड के साथ इंट्रोड्यूस कराते हैं. तो केमिस्ट बोलते हैं कि भैया अगर हम केमिकल रिएक्शन नहीं करेंगे तो आप लोग नाउअडेज इससे कोई बड़ा नहीं. जिसको अंग्रेजी आती है उसको हम नकार देते हैं कि भैया भारत अब भारत बनने जा रहा है. इसलिए मैं भी बीच बीच में हिंदी बोलने का प्रयास करता हूँ. तो जब मैं विदेश से वापस आया था तो मेरे से भी हिंदी बोलना बहुत कठिन लगता था मुझे, अभी भी लगता है, लेकिन अब क्या करें, समाज बदल रहा. फिर जो फिजिक्स केमिस्ट्री मैथमेटिक्स की जो बाउंड्री थी, नाउ विद द न्यू डेवलपमेंट ऑफ साइंस एंड टेक्नोलॉजी we have to shake hand with each other, then we can. So तभी chemical modulation of valence band. So we have to modulate the flat band of valence band. We have to modulate it. How? Chemically. How we can do? Theoretically we can write the quantum equations or all this kind of equations we can write. But रियल साइंस का बच्चे पूछ रहे थे कि भारत में इलेक्ट्रॉनिक चिप नहीं बनती है, ये नहीं बनती है. हमारा पैराडाइम ऑफ थिंकिंग वाज रॉन्ग. हम उस आदमी को महान कहते थे जो कहता था मैं क्वांटम कंप्यूटेशन की कैलकुलेशंस करता हूँ. आई एम ए थ्योरेटिकल फिजिसिस्ट, उसकी बहुत इज्जत हुआ करती थी. जो एक्सपेरिमेंटलिस्ट मेरे जैसे होते थे ना, इनको लोहार कहा जाता था कि ये गोल्ड स्मिथ हैं, ये लोहार हैं. आज जमाना तभी भारत पिछड़ रहा है. हमने ज्यादातर समय थ्योरेटिकल रिसर्च के ऊपर व्यस्त किया. जब तक हम अपनी उंगलियां लेबोरेटरी में नहीं जलाएंगे, अपने कपड़े गंदे नहीं करेंगे, तब तक देश में टेक्नोलॉजी नहीं आ सकती. So that's why The chemical modulation of valence band was a theoretical idea, but how we can realize that? The mixing of orbitals. How we can mix the orbitals? Basically, we are doing some kind of a substitution of the material. So we have to synthesize the materials chemically. So there is a concept of physics, concept of quantum mechanics, and the role of chemists to really do that. तो सारे गुण सर्वगुण संपन्न 16 कला संपूर्ण तो भगवान कृष्ण थे. So we have to do a collaborative research. If we really want to do something good, we have to perform the collaboration, which is a material engineering, physicist, chemist, synthesizer, device maker, all the things. लेकिन आज मैं जो शो करने जा रहा हूँ, हम 3 लोगों ने इस काम को, जैसे मैंने फर्स्ट स्लाइड लिखा, डॉक्टर विक्रम वर्मा, जर्नैल सिंह वाज आवर पीएचडी स्टूडेंट, 3 लोगों ने इस डिवाइस को एंड तक लिखा. So we thought that our the thought process, we designed some kind of material. Sometimes most of the researchers, because आप सब लोग young researcher हो, मैं जिस लेक्चर का मतलब मेरा अपने रिजल्ट दिखाना नहीं है, to motivate you guys. हम लोग देखते हैं लकीर का फकीर होते हैं. आपके गाइड भी होंगे, अरे कोई पेपर ढूंढो, उसमें थोड़ा सा वेरिएशन करो, ये कर दो, वो कर दो, और फिर बोलते हैं ओरिजिनल रिसर्च करें. तो हम तो किसी बने हुए घर में थोड़ी सी डिस्टॉर्शन अपसाइलन चेंज करके रिसर्च पेपर छापते हैं. उससे कुछ नहीं होगा. लिटरेचर बढ़ेगा, लाइब्रेरियों के ऊपर भार बढ़ेगा, उनकी बुक्स बढ़ेंगी, कहीं गिर भी सकती हैं. So what you do? Think out of the way. When we started this problem, I started with the chromium oxide. I don't know how it came occur to me, because I was, as I told you, I was a man trained in magnetism. So chromium oxide is anti-ferromagnetic insulator. That is called Mott insulator, which has a band gap of 3.1 electron volt, and most stable that chromium can form is Cr2O3 crystallized in a corundum structure with hexagonal closed packed layers of oxygen atoms and 2/3 of the octahedral sides filled with the chromium atoms with the primitive cell. अब हम प्रिमिटिव एंड नॉन प्रिमिटिव सेल भी पढ़ते होंगे. आप जब क्रिस्टल तक के पट्टोजानर्सी के बच्चे हैं, फाइनल ईयर बीएससी के बच्चे हैं, किटल जहाँ कोई ना कोई किताब पढ़ते होंगे, भारतीय किताब पढ़ते होंगे, जहाँ विदेशी किताब पढ़ते होंगे, उसमें हम लैटिस स्ट्रक्चर की बात करते हैं, प्रिमिटिव एंड नॉन प्रिमिटिव स्ट्रक्चर. तो सारी चीजें आप लोगों को मैं रिमाइंड करा रहा हूँ, आप लोग पढ़ते हो, पर नई चीज नहीं. The primitive unit cell is rhombohedral with crystal parameter, lattice parameter for around 5 angstrom and around 13.6 angstrom or so. And this is a structure. Now, why I have selected this structure? This is a very nice layered structure. I have an oxygen layer. I have a chromium layer. Now I want to modulate the chemical valence band. How I can do? I can easily do some substitution and modification. Then proper substitution to reach again. कभी भगवान की दया हो, लोग बोलते हैं साइंटिस्ट भगवान को नहीं मानते. मैं कहता हूं कि बिना भगवान में आस्था रखे साइंस हो ही नहीं सकती. Now I will tell you what is भगवान for me. ये नहीं कि मैं किसी मंदिर में या किसी बाबे का चेला बन जाऊं. I should love nature. Nature is a God. And why we never say search, we say research. Mother Nature has given us everything, and we are exploring that. That's why it is called research. यहाँ तो present है, सब कुछ available है, हमें आँख चाहिए, हमें ऐसा कर्म करना चाहिए कि उसको एक्सप्लोर करते हैं। वही भगवान की भक्ति है। सुबह भी बुजुर्ग बैठे थे, कहते कि भगवान में पता नहीं साइंटिस्टों की आस्था होती। मैं कहता हूँ बिना भगवान की आस्था से, जहाँ विदाउट लविंग द मदर नेचर यू कैनॉट डू दैट। बिकॉज जिस चीज के विपरीत जाओ, जिसमें सब कुछ विद्यमान है, उसके विपरीत जाओगे तो वो आपको बख्शेगा नहीं। किसी की भी विरोध करोगे तो वो आपका भी विरोध करेगा ही करेगा। तो अगर उससे प्यार करोगे तो उससे सब कुछ ले लोगे। तो इसलिए ये जो भावनाएं थी ना कि साइंटिस्ट कॉमरेड होते हैं, भगवान को नहीं मानते, ये गलत थी। और तभी कुछ बना नहीं भारत का, ज्यादातर कॉमरेड डोमिनेटेड साइंस से ही बना। So now we are nature lovers doing that kind of thing. तो हमने ढूंढ किया, नेचर को ढूंढा, तो देखा कि ये कैसे बन सकता है मटेरियल। So then I straightforward come to my experiment. हमने पहले बहुत ट्राई किया कि लिथियम, मैंने पिछली स्लाइड पे बताया, बहुत कुछ किया, कुछ नहीं बना। Then one day साइंटिस्ट कई बार कहते हैं अकेले में बैठते हैं, चिंतन करते हैं। चिंतन का मतलब जैसे महात्मा पहाड़ों में चिंतन करते हैं, गुफाओं में चिंतन करते हैं, कुछ पाने के लिए, ज्ञान पाने के लिए। ऐसे हम लोग समाज में रहते हुए, अपने लोगों में रहते हुए, अपने दफ्तर में बैठ के चिंतन करते हैं, अपनी लेबोरेटरी में चिंतन करते हैं। तो जब चिंतन कर रहे थे तो हमने सोचा कि मॉड्यूलेशन करनी। पहली तो बात है कि अगर एटॉमिक रेडियाई ऑफ माय मटेरियल आर मैचिंग, तो एक दूसरे की जगह ले लेंगे ना। अगर उनका इलेक्ट्रॉनिक स्ट्रक्चर डिफरेंट है, साइज सेम। पहली तो बात है कि एक चेयर पे बहुत पतला आदमी बना बिठा दो तो भी बुरी लगती है। एक बहुत मोटा आदमी, अभी सुबह गलती देखा था, थोड़ा छोटे भाई, वो भी चेयर पे बैठा दो, चेयर फैलने लगती है। तो ये रिक्वायर है ऑप्टिमम साइज ऑफ द चेयर, आइटम। अस्सी में मजा लेना चाहिए, तो फिर साइज सभी समझा। ऐसे सब्स्टिट्यूशन करते वक्त वी हैव टू सिलेक्ट द प्रॉपर atomic oblique ionic size of the substituent with different electronic behavior. पहले तो मैं उसको बिठाऊंगा, फिर उसको बोलूंगा हलचल कर। तो बैठेगा, अगर प्रॉपरली नहीं बैठेगा तो हलचल ज्यादा गलत हो जाएगा, तो स्ट्रक्चर चेंज हो जाएगा। स्ट्रक्चर को मेंटेन रखते हुए इलेक्ट्रॉनिक मॉडिफिकेशन और ऑर्बिटल engineering we have to do. So what is that? Look at the chromium and magnesium, look at the chromium and aluminum, look at the chromium and nickel. Their ionic radii are almost matched, but their electronic structures are different. तो काम तो इलेक्ट्रॉन ने करना है, ऑर्बिटल ने करना। पहले बैठ जा, फिर पंगा ले। तो उसको बिठाने का प्रयास करने के लिए, एंड देन अगेन एक डाइवेलेंट है, एक ट्राइवेलेंट है। एल्यूमिनियम इज अ ट्राइवेलेंट कैटायन, मैग्नीशियम इज अ डाइवेलेंट कैटायन, एंड जो निकल है ना, बदमाश है। व्हाई निकल इज बदमाश? ये डाइवेलेंट भी है, ट्राइवेलेंट भी। कहता है जहां जैसे मर्जी मुझे इस्तेमाल करो। तो हमने कहा कि एक शरीफ ले लेते हैं, दूसरा भी शरीफ ले लेते, तीसरा बदमाश ले लेते हैं, तो कोई ना कोई तो पंगा करेगा। That's the way the science learn. Experimentals are doing this way science. हम हैमिल्टनियन नहीं देखते हैं, बाद में देखेंगे। पहले हम देखते हैं मोटा, पतला, ताजा, ये वो, बदमाश, शरीफ, सब कुछ देखते हैं। So that's what we are doing. when here, then how to synthesize? The easy way, Dr. has told so many synthesizers process forming. I will tell you nano materials, nano fabrication. Morning, Professor Shashi was asking me a sol-gel. मैं कोई बात नहीं हम बताएं. So we are using a simple chemical route of synthesization of material. लोग बोलते हैं साइंस करने के लिए पता नहीं बड़ी लेबोरेटरी चाहिए, बड़ा इंफ्रास्ट्रक्चर चाहिए. I will tell you, with 4-5 beakers you can do the science with a simple chemical. That's what is a nanotechnology and nanoscience is going. So to do this kind of material, we use the co-precipitation method. अब बोलोगे co-precipitation method क्या है? नाम बड़ा लगता है ना, दक्षिण कोटि. कुछ नहीं, आपके पास 3 चीजें चाहिए. क्रोमियम बेस्ड कंपाउंड चाहिए, कुछ मैग्नीशियम बेस्ड कंपाउंड चाहिए, या एल्युमिनियम बेस्ड कंपाउंड चाहिए, या निकल बेस्ड कंपाउंड चाहिए. तो आप क्या करते हो? क्रोमियम क्लोराइड ले लो, क्रोमियम नाइट्रेट ले लो, क्रोमियम एसिटेट ले लो, जो भी आपकी लैब में अवेलेबल है ले लो. क्लोराइड, नाइट्रेट, एसिटेट. सेम मैग्नीशियम का क्लोराइड, नाइट्रेट, एसिटेट. सेम निकल का कोई. क्यों ले लो? क्योंकि ऑक्साइड इनके सॉल्युबल नहीं होते. ऑक्साइड को पानी में घोलोगे नहीं घुलेगा, क्लोराइड घुल जाएगा, एसिटेट घुल जाएगा, नाइट्रेट घुल जाएगा. तो जो वाटर सॉल्युबल हो, क्लियर सॉल्यूशन बना लीजिए, ट्रांसपेरेंट क्लियर सॉल्यूशन. अब इनमें क्या होगा? क्रोमियम के आयन होंगे, क्रोमियम हाइड्रोक्साइड बन जाएगा, साथ में एसिटेट एसिड बन जाएगा, उधर नाइट्रिक एसिड बन जाएगा, क्लोराइड है तो HCl बन जाएगा. तो जब किसी मटेरियल में एसिड है, व्हाट एसिड इज डूइंग? इट इज कटिंग इट. कपड़े पे डल जाए कपड़ा साड़ देता है, हाथ पे डल जाए. So it is cutting that. So you will get a nice transparent solution, but it is acidic in nature. You measure its pH value, it is highly acidic. 1.5 pH value आ जाएगी आपकी. ये सारे solution. Now I have to make a stoichiometry. Stoichiometry means how many atoms of chromium I want to replace with the magnesium or aluminium or nickel. तो मैं उसी हिसाब से केमिस्ट्री यहाँ आ गई, मोलर सॉल्यूशन. तो हम सभी का सेम मोलरिटी का सॉल्यूशन बनाएंगे. Why? In 1 molar solution, how many moles are present? So number is remaining constant in 1 mole solution. अब मैं इसका 100 ml ले लूं, इसका 10 ml ले लूं, तो मैंने बताया कि 10% एटम मैंने चेंज कर दिया. Depending upon my way, how much I want to change. सिंपल चीज है, किसी को कोई शंका तो नहीं. अब ये सारे एसिडिक. अब हमने एसिड को रिड्यूस करना है और मटेरियल को प्रोड्यूस करना. सो व्हाट आई विल डू, एसिड को रिमूव करने के लिए क्या चीज चाहिए? सब लोग +2 में बेस चाहिए. तो बेसिक सॉल्यूशन क्या होता है? सोडियम हाइड्रोक्साइड, अमोनियम हाइड्रोक्साइड, or any other kind of base you can take. Now you put a drop by drop of the base and they start precipitating. आपको बड़ा यार देखो कितना अच्छा लगा. कुछ चीजें देखने में खुशी प्राप्त होती है. अब यही मैं कहता हूँ इलेक्ट्रोडायनेमिक को इक्वेशन लेके बैठ जाओ, कितना मर्जी सॉल्व करते रहो और आपको मजा नहीं आएगा. The moment they put a drop, you see some precipitation. So that's the beauty of the experiment. So you can make. Now these precipitates are solid, and you see at what you can control the size by changing the acidity of the material, means pH value. ये लैब में कर सकते हैं ना आप लोग.
अब बीएससी में प्रोजेक्ट करिए, एमएससी में प्रोजेक्ट करिए, पीएचडी तो लोग बहुत लोग करते ही हैं, बाद में जो देखेंगे तो आपको अच्छा लगेगा कि देखिए मैं सामने बन गया। यूज क्या कोई बड़ी मशीन नहीं यूज की, बीकर है, पानी है, केमिकल है सस्ते, आधा किलो 2000 रुपए का आ जाता है जब केमिकल जिसमें बात करता हूँ। तो आपको चाहिए कितने ट्यूबलैंड, चवानियों से लिए में काम हो जाता है ना। आजकल तो रुपयों में होता है, हमारे टाइम पे चवानियां रुपया बहुत बड़ी बात होती है। तो ये चीजें देखिए कितनी सिंपल चीज है, एंड यू गेट दैट पार्टिकल। उसके बाद है सेपरेट करना, यूनिवर्सिटी लेवल सेंट्रीफ्यूज होता है ना, घुमा के, नहीं भी है तो कोई बात नहीं, पड़ा रहने तो पार्टिकल नीचे बैठ जाएंगे। नितार लो, जैसे घर में चावल से पानी नितारते हैं ना, आपकी मम्मियां जब चावल बॉयल करती होंगी तो पानी निकाल देती हैं, जिसको पिच बोलते हैं पंजाबी में, मांड बोलते हैं कोई और भाषा में। तो वो चीजें हैं। तो यू कैन आल्सो डू सिंपल, देन यू हैव टू ड्राई इट। ओवन होंगे आपकी लैब में, ड्राई करो, यू विल गेट इट पार्टी। सो नैनो टेक्नोलॉजी इज सो सिंपल। ओनली हम लोग जब बड़े बड़े शब्द यूज कर देते हैं ना, डरा देते हैं बच्चे, तो ऐसा शब्दों के पीछे मत जाइए। सो वी कैन प्रिपेयर दोज काइंड ऑफ नैनो पार्टिकल्स ऑफ दोज मटेरियल। अब सुबह डॉक्टर साहब ने बात करी थी कि भाई इतना कुछ कर दिया, दिखने में बड़ा सिंपल है, कि बना भी है क्या? ये चीज जो हम सोच रहे थे पैदा हुई कि नहीं हुई, कि हमें बकवासगिरी होगी, सारा कुछ चूर्ण मिल गया कोई, वो चूर्ण है क्या? पाउडर जिसको बोलते हैं अंग्रेजी, ठीक है। तो पाउडर को कैरेक्टराइज करने के लिए फर्स्ट कैरेक्टराइजेशन इज द स्ट्रक्चर ऑफ द मटेरियल। हाउ वी कैन डू? We can do using X-ray diffraction. Second is the molecular structure of the material and the structural symmetry of the material. That can be done by Raman spectroscopy and IR spectroscopy. अब आप बोलोगे कि IR और Raman में क्या? If you have a permanent dipole present, तो IR कर लेंगे डाइपोल की रेजोनेंस देखने के लिए, कौन कौन सी वाइब्रेशनल फ्रीक्वेंसीज है, कौन कौन सी बॉन्ड है, इज अ डबल बॉन्ड, ट्रिपल बॉन्ड और ऑक्टाहेड्रा और टेट्राहेड्रल स्ट्रक्चर और एनी काइंड ऑफ सिमेट्रीज आर देयर। अगर कोई नॉन पोलर सिस्टम हो, व्हाट वी कैन डू, देन वी हैव टू इंड्यूस द पोलराइजेशन। द इंड्यूस्ड पोलराइजेशन इन अ नॉन पोलर सिस्टम बाय some light. That's what Raman Sahab got Nobel Prize. That was the first Indian Nobel Prize. मैं भारतीय साइंस को बहुत बढ़ावा देता हूँ इसी बात पे कि हमारे भारतीयों के किए हुए काम आज हम यूज करते हैं। तो he made the Raman effect, that induced polarization light by the coherent electromagnetic radiation. And now dipole बन गया। अब फिर हम उसकी शिफ्ट देख लेते हैं। Raman shift has Stokes and anti-Stokes, and then we can see what kind of wave numbers are coming, so we can look at the structure, molecule structure. Then if you look at the band gap, so you have to pass the light. Which light can be transparent, at which they will be absorbed, that's the band edge of that thing. So we can find out the band gap by, and we are looking at the transparency also. Then this way you can do the characterization of the material. We did that characterization. I will show you some of the results. This is the X-ray diffraction. And X-ray diffraction results we can do, and there is a Bragg's peaks are there. And each and every Bragg peak will characterize the different planes with a Miller index HKL. And they are a family of the material planes in a material. And what is the spacing between the two consecutive planes is the D, and 2D sin theta ब्रैग साहब ने दिया है। अब मेरे पास थीटा वैल्यू आ गई, लैम्डा मुझे पता है इक्वल टू n lambda is the wavelength of my X-ray. So I can easily find out what is the D spacing and what are the HAL and what is that plane. Now, in that, we don't know the intensity of different peaks. Now, the intensity of that peak depends on how many number of atoms, cations are present into the plane. That will affect the density of electron into the system, which can scatter that kind of. एक सिंपल चीज है, उसको देखने के लिए स्ट्रक्चर फैक्टर की बात करते हैं, आपने पढ़ा होगा। मैं इसलिए साथ साथ ये चीजें बता रहा हूँ कि आप जो सॉलिड स्टेट फिजिक्स में पढ़ रहे हैं उसको हम कैसे इस्तेमाल। If I know the structure factor, I know I can then intensity भी देख सकता हूँ। Structure factor is number of in that plane and in the structure, atom कितने हैं, ion कितने हैं। So that is the Redweld analysis. So we perform the analysis completely, not simply। बहुत सारे लोग क्या कहें, ओ जी पीक कहाँ आ गया, पिक्चर बन गया। नहीं भाई, पीक तो आ गई, क्या ये रियल पीक है? Is it matching with that? So that you have to do the Redweld analysis. That's what we performed, and we found that the single phase substituted material we can get. Same we did with the magnesium, same we did with the aluminium, same we did with the nickel. Then another analysis, then to see when you are substituting the material, you have a strain into the system. And that strain will depend upon the particle crystallized size also. Either you can find out from a Scherrer relation of the MHRD, or you can do with the TM or SEM. So with this Raman spectroscopy we did, as I explained you, UV visible. So various materials we are doing all these kind of things. The basic philosophy I have explained. Now come to the, madam, give me 10 minutes, that's all. Now we have made a powder. Powder से डिवाइस बनती है? नहीं भाई, किसी हकीम की पुड़ी तो जरूर बन सकती है, लेकिन powder से डिवाइस नहीं बनती। So we have to make a device. Morning, Dr. Saab has told you many techniques. Here we are using a pulse laser deposition technique, which I have established at NIT Hamidpur, where we can grow the epitaxial film. You see the epitaxial, the layer by layer growth, it means the single crystal over some single crystalline substrate. So we see that is a single crystalline, all the films with the different compositions. Then epitaxy, the strain epitaxy, how if the lattice of this, that's the expansion in the C-axis. The total volume of the lattice should be conserved. So what kind of strain? You have a compressive strain or tensile strain that you can measure. To measure that, you have to make a 5-scan. X-ray will be oriented in a C-axis, you will get a C-axis. Whether they are having a AB plane epitaxy, so you have to do the 5-scan of the measurement. So that's what we are producing. They are single crystalline films. Then there is an electronic structure we are studying with XPS. I will not come to that. I may come to the devices. You see, these materials are having a very good transmittance of 80% and 70 to 80% or so. अगर देखना है तो भाई सब सीधा आंख से भी देख सकते हो। फिल्म को किसी अखबार पे रखिए, उसके ऊपर से अखबार पढ़ लो, इसका मतलब ट्रांसपेरेंसी गुड। ना ही तुम्हारे पास कोई इंस्ट्रूमेंट हो तो आप सीधा कह सकते हो ट्रांसपेरेंसी है। तो मैंने दोनों तरीके से दिखाई आपको, सेम बात दूसरे मटेरियल पे, तीसरे मटेरियल पे। देन वेदर they are conducting or not. So morning Dr. I told you to measure the electrical conductivity using a 4-probe method, and you can find out the resistivity, and the inverse of the resistivity is the conductivity, and using some, then you do the Hall measurement to find out what is the Hall mobility, whether the carriers are p-type or n-type, depending on R factor, RH factor, positive or negative. So we found that they are p-type. Their conductivity is very good, and their Hall mobility is reasonably good. So I will show you the table. You see, the resistivity is of magnesium system is 3.36 ohm centimeter. बहुत अच्छी लो रेजिस्टिविटी सेमीकंडक्टर की लेवल की इतनी होती। दे आर पी टाइप एंड देयर हॉल मोबिलिटी इज वेरी लेस, whereas in nickel case the resistivity is 1.36 ohm centimeter, very good, and hall mobility is 4, which is also good for the passive devices. And overall figure of merit we are calculating by optimizing the properties, and we found that 34.62 is a figure of merit in this case. And then we compare कि दुनिया में जो लोग इन काम में लगे हुए हैं, क्या हम उनसे अच्छे हैं कि बुरे हैं? So you compare with the literature. So our work is showing you the highest value of figure. So we started with the powder, making a powder, end up with the device. So we can say, वो लड़की पूछ रही थी पिछले साल से कि भाई भारत क्यों पिछड़ा हुआ है, मैंने बीच में उसका रीजन भी बता दिया। हमारे साइंटिस्ट किसी प्रोजेक्ट को लेते हैं, जब तक पब्लिकेशन नहीं आती, चाहे आ गई तो वहां छोड़ दे, प्रोजेक्ट लो, एंड तक कंप्लीट करो, तभी उसका फायदा। हमने स्टार्ट किया था टॉप को ट्रांसपेरेंट कंडक्टिंग ऑक्साइड पी टाइप मटेरियल। मैं चाहता था पाउडर पे छोड़ देता गेम, चाहता तो थिन फिल्म पे छोड़ देता गेम। नो, आई टुक 6 years or 5 to 6 years to complete this project. और आज मैं गर्व से कहता था, कोई इंडस्ट्रियलिस्ट मेरे पास आए, मैं उसको नो हो बता सकता हूँ, क्योंकि मैं इतना काबिल नहीं, मास्टर आदमी हूँ, पैसा नहीं है, इंडस्ट्री लगा नहीं सकता। ठीक है, but if somebody will come, even government of India wants, I can give them no. How to make that of those kind of things. So that is the thing. We started the material with a different kind of materials and end up with the, this is the conclusion of my talk, and I will leave the my slides with this to distribute to the students, those who want to understand these in depth. And thank you very much for your kind attention. Any question, any doubt, you are most welcome.
Thank you so much. Sir.
ये बेटा स्टार्टिंग सोल्यूशन है, कुछ भी ले लो, मटेरियल अंत में वही बनेगा, चाहे आप क्लोराइड से स्टार्ट करो, चाहे आप एसीटेट से स्टार्ट करो, चाहे आप नाइट्रेट से स्टार्ट करो, अंत में सॉल्यूशन वही बनेगा जो हम चाहते हैं। क्योंकि क्लोराइड बनेगा तो जो एसिड बने HCl बनेगा, which we want to remove it and wash it over ठीक है, किल करते हैं जीन डाल के, एसीटेट यूज करेंगे तो एसिटिक एसिड बनेगा, अल्टीमेटली मेरा वो मटीरियल तो बनेगा। और आपका प्रश्न? हाँ,
दोनों सेम एसिड होने चाहिए।
यस, ये नहीं, ठीक है ना। अगर सपोज करो मेरा क्रोमियम भी एसीटेट है और मेरा मैग्नीशियम भी एसीटेट, तो ठीक है। ये नहीं एक का क्लोराइड ले लो, दूसरे का नाइट्रेट ले लो, तो HCl और HN मिल के क्या बनेगा? एक्वा रिजिया। केमिस्ट्री पढ़ी है, एक्वा रिजिया इज मोर किलर देन एनी अदर एसिड, ठीक है ना। तो दो नेम एक ही तरह का, क्योंकि बेसिकली रिएक्शन को समझिए, दो एसिड मिलेंगे आपस में तो भाई झगड़ा तो करेंगे, कुछ ना कुछ तो ना होगा, ठीक है। वो गलती नहीं करने का, दोनों सेम रखने का। जो होस्ट का और किसी का कोई क्वेश्चन? हाँ बोल, मुझे कोई दिक्कत नहीं है, मैडम कहूंगी जी। तो ये लेट आई हैं, अब आके मुझे फट्टा देना है, वो वाला जो टोकन है तो उसके लिए आई है, तो ये लेट का हूँ आप मुझे हाँ जी हाँ। देखिए बेटा, व्हाट वी आर मेजरिंग विद रामन, बैंड गैप तो नहीं मेजर सकते हम। क्या करते हैं? इंड्यूस पोलराइजेशन करते हैं, बैंड गैप देखना यूवी विजिबल करते हैं। तो इसलिए जो लेजर है, लेजर कैसी लेजर लेनी चाहिए विच इज कैपेबल ऑफ इंड्यूसिंग द पोलराइजेशन इनटू द सिस्टम। जैसे 514 के करीब लेते हैं लेजर हम, और डिफरेंट बहुत सारे लोगों के पास जैसे जैसे लेजर मिलेगा। आई हैव 3 टाइप ऑफ लेजर इन माय लैब, so with different materials we are using a different kind of।
तो बेसिकली मेरा क्वेश्चन ये है कि ऐसा तो नहीं है कि ये वाले बैंड गैप वाले मटेरियल्स हैं तो उनका रमन नहीं आएगा ये भी लेजर से, या ऐसा?
देखिए रमन मोड, एक्टिव रमन मोड किसके आएंगे? which has a center of symmetry। if you have a non center of symmetry then IR is sufficient because the material become polar, समझे? तो वहां वो और कुछ पूछना? हाँ बेटा, पॉलिटिकल क्वेश्चन नहीं, because I avoid politicians।
Sir, like I'm a student of biochemistry.
Very good।
So, but while listening to you, listening to all of this talk, the first thing that came to my mind was that can we use this in advancing medical imaging?
Just basically medical imaging, basically you have to do either through NMR, because you are using with a tissues। basically what we want, MRI एक्सरे से हड्डियां हो जाती हैं, तो टिश्यू पे हड्डियां एक्सरे नहीं काम करता, तो वहां हम क्या करते हैं? प्रोटॉन NMR या कार्बन NMR, because all the tissues are made up of proton, carbon and hydrogen, nitrogen, sulfur, these kind of polymeric systems। so here we are using the different isotopes of the carbon and hydrogen, and then we are taking a magnetic resonance of that, तो वहां NMR। लेकिन आप बायोकेमिस्ट हो, मैं तेरे से क्वेश्चन कुछ और एक्सपेक्ट कर रहा था, is it possible we can make these kinds of material by plant extraction? बहुत सारे प्लांट जो हैं जिनमें अलग तरीके के केमिकल, उन प्लांट्स से ग्रीन केमिस्ट्री करके we can extract those kind of things, and I am evaluating the thesis of some Brad of this institution, Shilpi Brad, she has done very good work on abstraction of the biological system। I don't know इसका गाइड कौन है, यूनिवर्सिटी के गाइड नवदीप गोयल हैं, तो मेरे पास तीसरा मैं कुछ दिनों में, and I am very impressed from the work because one guide is from your FC college. तो मैं देख रहा था पेपर पढ़ा कि कितनी अच्छी इनोवेशन की है कि प्लांट एक्सट्रैक्शन से टाइटेनियम ऑक्साइड बनाया and that titanium oxide is used for drug delivery. तो मैं तेरे से ऐसे क्वेश्चन कर रहा बाकी वो जो तुमने पूछा से NMR CT scan those kind of images.
सर जैसे अभी रिसेंटली कुछ टाइम पहले पेटेंट किया है जापान की कंपनी ओस्कोसा ने कॉग्निसेंट के साथ मिलकर वो टैबलेट्स है जो कि वो पेशेंट्स को देते हैं और उससे जो दवाई है उसके प्रेजेंस को ट्रैक करते हैं.
That's a drug delivery.
Yes sir.
That's what drug delivery, but we are encapsulating the drug in the nanoparticles.
Yes. So
those nanoparticles, if they are in magnetic in nature or they have a thermal properties, wherever the disease, वो कहीं नहीं drug को release करेगा. It requires a condition to release. For example, जहाँ भी आपकी बॉडी में कोई इंफेक्शन होता है, at that part the temperature of the body is high. देखिए ना, अब कई बार कहते हैं कि इंफेक्शन होगी, हमें बुखार होगा, अल्टीमेटली वो उस पार्ट का टेम्परेचर बढ़ा, धीरे धीरे आपकी बॉडी का टेम्परेचर बढ़ा देता है. तो जब मैं ड्रग डिलीवरी कर रहा हूँ, तो at certain temperature the drug is released from the particle. And that also in a controlled way. बाकी जो ड्रग है जो नहीं रिएक्ट की वो मलमूत्र बन के बाहर. तो वो एक टेक्नोलॉजी है. Not only Japanese, this technology we have in India also, drug delivery, and that Shimpi Brad, जगह में ना ठीक है. That Shilpi Puller has done a very good experiment in vivo, in situ, something like that. So she has done good work.
so this material can just be used for like internal angiography because it's transparent, it is conducting, and if we can
That
extract it.
research I will leave on you. I have given you material. Now you think over this thing. Okay. Any other question? क्यों मुंडिया को कोई क्वेश्चन नहीं, सारा कुड़िया ही पढ़नी है आजकल. कहते हैं गेड़ी गुड़ी पे रहने हो.
There is one.
हाँ, शाबाश सरदार जी. दिल कर दिया.
So are there new applications that Peter Semiconductor introduced that anti-semiconductors can't do?
Yes.
I mean,
देखिए, अगर मैं कहूँ आपको एक पीएन जंक्शन बनाना है या डायोड बनाना है, तो डायोड बनाने के लिए कल्ला एन तो नहीं चाहिए, साथ में पी भी चाहिए. ठीक है ना. पहले मुंडे मुंडे का ब्याह आजकल तो हो जाता है, मुंडे कुड़ी का ही ब्याह होता ना, तो इसलिए पी भी चाहिए, एन भी चाहिए. तो जो जंक्शन बनेगा, डिप्लीशन बनेगा, डायोड बनेगी. ऐसा ही ट्रांजिस्टर बनाना तो तेन एन भी चाहिए, पी भी चाहिए, एन भी चाहिए, या दोनों चाहिए ना. इसलिए माय फर्स्ट स्लाइड वाज इनविजिबल इलेक्ट्रॉनिक्स. When both P and N will be transparent, then we will have invisible transparent.
Or if we want to manufacture, let's say, Peter Semiconductor, is it less costlier than producing anti?
देखो जी, जिस तरह के मटीरियल की सरदार जी ਆਪਾਂ ਗੱਲ ਕੀਤੀ ਹੈ, ਅਸੀਂ ਤੁਹਾਨੂੰ ਦੱਸਿਆ ਕਿ ਚਵਾਨੀਆਂ 'ਚ ਬਣਦਾ, ਪਈਆਂ 'ਚ ਬਣ ਜਾਂਦਾ. ਅੱਜ ਕੱਲ ਚਵਾਨੀਆਂ ਦਾ ਜ਼ਮਾਨਾ ਚਲਾ ਗਿਆ. ਮੈਗਨੀਸ਼ੀਅਮ ਕਲੋਰਾਈਡ 2000 ਰੁਪਏ ਦਾ ਅੱਧਾ ਕਿਲੋ ਮਿਲਦਾ ਹੈ. ਤੇਰੀ ਇੱਕ ਥਿਨ ਫਿਲਮ ਦੇ ਵਿੱਚ ਕਿੰਨਾ ਕੁ ਲੱਗਣਾ? ਮਾਈਕਰੋਗ੍ਰਾਮ or 1 gram, let's say, because film total is in a microgram.
Yeah.
So that is much cheaper. Whether you make N or P, material cost is not too much, not matter. Only the fabrication cost will be met. So that also much that simple way than the semiconductor technology. अभी morning वो कितने बड़े-बड़े तरीके आपको बता के कि त्रिपाठी जी वो चलोस्की मेथड, ब्रिजमैन मेथड, फलाना मेथड, इधर तो हम विक्रो में बात करते हैं. 3 बीकर कितने के आएंगे? 10 रुपए का आ जाता होना, जब 20 रुपए का बीकर 100 रुपए 100 का है 150 का। हाँ मेरा तो लैब अटेंडेंट टीचर, मैं कभी उससे पूछा नहीं कितने में बिल डिसाइड करता हूँ, तो 150 रुपए का एक 4 1000 रुपए के अंदर तुम्हारी लैब सेट करा दी मैंने, है ना? जितने मर्जी पाउडर पर नाम बन जाओ और कुछ। वेरी गुड, आई फाउंड दैट वन बॉय हैज और कोई क्वेश्चन नहीं? चलो कुड़ियां से आगे कोई गल। आई एम नॉट ए जेंटल सेलेक्टिव। ठीक है?
I'm sure everyone has enjoyed the talk like anything. So let's thank the speaker once more. Now I invite Dr. Neelu to kindly present and Dr. Sanjeev to present the photo.
Just I am joking, man. My email address you must have noted down. Any query, any question, any time. देखिए जितना फ्रेंडली लेके साइंस कर सकते हैं ना, कई बार क्या है टीचर ऐसे बच्चा वैसे डरता रहता है, तो फ्रेंडली टीचिंग आपकी सीखोगे, आपके अंदर भय नहीं रहेगा क्वेश्चन पूछने। एंड सेकेंडली कभी टीचर को इंसाइक्लोपीडिया मत समझिए, हम लोगों को भी लिमिटेड नॉलेज है। वी आर आल्सो लर्निंग थ्रू योर क्वेश्चन। हो सकता है हमें आंसर आता हो, कई बार हमारे जो टीचरगण बैठे हैं इधर से सब मेरे कुछ स्टूडेंट भी रहे होंगे, कहीं मैंने लेक्चर भी सुने होंगे। ये चीज है कि भाई अब चीजें मुझे नहीं आया, मैं 16 क्लास में स्टूडेंट नहीं हूँ, मैं भगवान कृष्ण नहीं हूँ। हो सकता है कि आपका जो क्वेश्चन हो मुझे विवश करे कुछ और सीखने के लिए। आई एम लर्निंग थ्रू यू गाइस। दैट्स व्हाई क्वेश्चन पूछिए, कोई बस आइडिया मिलता है। जैसे वो लड़की ने पूछा तो मुझे इमीडिएटली वो भुल्लर जी, मैडम भुल्लर का याद आ गया, तो बहुत अच्छा लगता है। तो देखिए, यू आर पेइंग टू लर्न, वी आर पेड टू लर्न। ठीक, हम दोनों ही रहे हैं, तो हमारे पैसे लग रहे हैं, हमें पैसे मिल रहे हैं, अंतर यही है। बाकी वी ऑल आर। तो खुश रह के पढ़ाया करो और खुश रह के पढ़ा करो, ठीक है?
Before we break for lunch, there is an announcement for the students who are going to present their posters. The poster session will be held during the lunch time only. The posters will be displayed in the Physics Department Seminar Hall, top floor. All of you know the space for that. So the participants of posters are requested to move straight away from the hall to the seminar hall and present their posters. Our esteemed guests will be evaluating your posters during the lunch time only. And lunch for faculty members and research scholars will be served outside the auditorium.
पोस्टर्स लगाने हैं सिर्फ, इवैल्यूएशन 2 बजे है, लंच करने के बाद ड्यूरिंग लंच 2 बजे इवैल्यूएशन।
You are now requested to just put up your posters for display. The evaluation for posters will be held at 2 p.m. after you have your lunch and refreshment. So at 2 p.m. the experts will come to evaluate your posters. As I just mentioned, for faculty members and research scholars, lunch is outside this auditorium only. And as far as students are concerned, for boys, lunch will be served in the boys' hostel only. And for girls, it will be served in lab number 3, Department of Physics. The students are supposed to show their coupons while having their lunch. You must have received in your registration kit. So we meet at sharp 2:30 to start the session in time. We'll be taking attendance at 2:30 so that no one of you runs away. Volunteers, please help the students move.
सेकेंड ईयर का अनाउंस करना है, मैं सेकेंड अपने कूपन ले ले।
MSc second year students, please collect your coupons. MSc second year hasn't collected their coupons.
Registration desk पे।
You can collect your coupons from the registration desk.
ग्रीन वेलकम करना है ना उनको।
मेरी बेटी ना ऐसे करे और मेरे को पसंद रेयरली आती है। अरे साइड से खींचो साइड से बहुत नहीं नहीं खींच रही ना मुझे पे साइड से साइड में आके करते हैं फिर ज्यादा लेट हो जाएंगे फिर जल्दी आएंगे पहले कूपन के ऐसी करती है क्या हुआ मुझे थोड़ा फोल्ड हो गया तो मुझे के लिए जाना है
हाँ हाँ कोड तो होगा उसमें। ये अभी सर की पेंसिल की है। ये जो अभी रवि सर की। हाँ हाँ ये
This one, are you going to use this one?
You can use either
Okay,
laptop
okay.
or connected.
But, oh no, you have both end open. अगर लैपटॉप पे अगर कनेक्ट होते हैं then it will be much convenient for me. Otherwise I have to copy and then.
We can यहाँ पे पेन है ना मैं उसको देखो मैं डाटा
चलो कोई ना मतलब इसको कॉपी नहीं किया जाता।
HDMI से कनेक्ट हो सकता है then I can use my laptop. Okay. Then it is better. मुझे
आपने कॉपी करना कॉपी हो जाएगा इसमें।
कॉपी से बेटर होगा क्योंकि मेरा ना मूवीज भी है।
HDMI है सर।
HDMI है। ऑडियो का ये है ना?
नहीं ऑडियो इसमें तो जो अपने पीपीटी चलाने इसमें ऑडियो तो
नो ऑडियो। हाँ मैं देख। Yeah, thank you. आ जाएंगे?
एक दो
वहाँ तो आ गए।
दोनों में आ रहा है बट प्रोजेक्टर में नहीं आ रहा है। तो मैं क्या कॉपी कर लूँ? कॉपी कर लूँ, इजी रहेगा आपके लिए। होपफुली मेरा जो वीडियो फॉर्मेट है वो आ जाएंगे। आई डोंट नो,
प्रोजेक्टर नहीं आ रहा, बाकी सारा
ठीक है, तो आप अपने सिस्टम में कर लो प्लीज, लेट मी कॉपी एवरीथिंग। इस फ्लोर में कोई वॉशरूम है? Okay. इसमें HDC बोल के एक फोल्डर है। आप कॉपी कर लो, इसे से लगा दो डायरेक्ट, ठीक। Look, I use है आपके पास? ना ना, ये लगा सकते तो कुछ नहीं करना पड़ेगा। It will work. No, not really, not really. Maybe here, is it okay? My laptop and other things. आपने इसका क्या वो लगा दिए थे? अगर ये नहीं काम करते तो कैसे करते हैं? ना, तो फिर इसको कैसे आप चेंज करते हो? Oh, thank you. No, thank you. हमारा मोबाइल का भीतर है आगे पीछे दर से ना जी नेक्स्ट ओके और मूवी क्लिक करना तो जस्ट क्लिक दैट ओके थैंक यू
मैम लेकिन हमें कॉल आई है, मेरे पास कॉल आई मेल भी नहीं आई पिछली बार फिर करा था बट मेरा मैसेज आया था
पता नहीं क्या था
इनका टॉप
प्लांट देने का अभी देना तो मैं यही तो करी हाँ
Good afternoon, everyone. I welcome all our esteemed guests and dear students to the second technical session of the fifth national seminar on recent advances in material sciences. The first talk of this session would be delivered by Dr. Shubhankar Chakravarti from INST Mohali, who would be talking about what is nano, why nano, how to make nano, how to see nano. Firstly, I would request Dr. Neelu and Dr. Sanjeev to kindly present a brief welcome to our distinguished speaker. I would now take this opportunity to introduce our eminent speaker to all of you. Dr. Chakravarti is working as Scientist E, Associate Professor at the Institute of Nanoscience and Technology, Mohali. He has been the founder head of Unit of Quantum Materials and Devices and Chairperson, Strategy and Planning. He obtained his MSc Physics from University of Calcutta and his doctoral degree from S.N. Bose National Center for Basic Sciences. His research interests majorly include designing and understanding the physical properties of new materials with integrated functionality for quantum materials, spin electronics, memory, and photovoltaic devices in the form of thin film, interfaces, and superlattices, to name a few. Dr. Chakravarti has been conferred upon with many awards and recognitions, such as 3 months fellowship to work at Upadhyay University, Sweden, by the Swedish Foundation for International Cooperation in Research and Higher Education, Best Presentation Award at Kinken Wakate, Japan, Melbourne Research Grant Award 2010 in Tokyo, Japan. He has acted as a PI and co-PI for a number of research projects. He has delivered many invited talks at various international and national conferences. He has more than 70 high-quality research papers to his credit. 6 PhD students have been awarded their degrees under his supervision. Presently, 6 PhD and 1 postdoctoral fellow are working in his laboratory. We are delighted to have you with us, sir. I would now invite Dr. Shivankar to kindly address the audience.
Yeah, I understand, but I have a habit to move and talk. Hand mic is very fine. Thank you. Okay. अब रख दीजिए if I need. So अच्छा पहली बात है आप लोग वहाँ क्यों बैठे हो I don't know. Why don't you come this side? वहाँ से कुछ दिखाई नहीं दे रहा है. अगर सोना है तो पीछे चले जाओ. अगर देखना है तो इधर आ जाओ. Which language you prefer? Don't say Punjabi because I'm sorry, but I can't speak. So in अंग्रेजी और हिंदी में एक choose कर लो, whichever you prefer. If I'm convenient with both of them, but तो कोई तो हाथ उठा के बोलो कि which language you prefer? पूरा हिंदी, पूरा तो नहीं बोल पाऊंगा. I have to use English in between. It will be mixed. पंजाबी तो नहीं हो सकता. I don't know. I'm sorry. Okay. तो ये सबसे संजीव जी ने सबसे डेंजरस टाइम दिया मुझे बोलने के लिए because this is the time after the lunch. You have a good lunch, then you want to sleep. So my duty is to keep you awake. That's it. So that you can listen to the next talk well. Okay. Thank you very much, Sanjeev ji, for this opportunity to discuss about briefly what we are doing in our institute. So I just want to give a brief kind of idea of the things we are doing in a very simplified manner. Okay, thank you. So this is what exactly we want to talk today. These are the very simple things. Number one, what is nano? Why nano? We are talking about nano so many times. And why nano? And how to make nano and how to see nano. So in case if you think that something you don't understand, कोई problem हो रहा है, then just stop me because otherwise it's a waste of your time and my time. So my name is Shubhankar Chakraborty. I am working at Institute of Nanoscience and Technology, which is located just 5-6 kilometers from here at Mohali. So the time is kind of around 30 to 35 minutes, right? Okay, so this is the first and only nanoscience research center in India by Government of Science and Technology, and this is under the Department of Science and Technology, Government of India. So I have been associated with few places. I did my MSc from Presidency College, Kolkata. Then I did my PhD from S.N. Bose National Center for Basic Science. I was there at Indian Association for the Cultivation of Science, Kolkata. Have you ever heard the name of this institute? You have been there. So except you, can somebody tell me the name of one scientist from this institute? They will be much bigger. Raman is from here. Yeah, Raman is everybody's teacher. You are doing Raman effect every day. Right? Yeah. So then I was in Indian Institute of Science, Bangalore for some time. After that, I was in Bar-Ilan University, Israel, as a visiting scientist. And very short period, I was there International Center for Theoretical Physics, Trieste, Italy. I was long time associated with Institute of Material Research, Sendai, Japan. Then I was an assistant professor at University of Tokyo, Japan, before coming to Mohali. So this is our newly built institute, and this is the building. It looks very beautiful, and it is actually very beautiful. So whenever you want, and if you're interested, please feel free to visit. It's not very far. It is located at Sector 81, Mohali. Okay. So yeah. We have institute in our institute have around 40 faculty members from the different field of research. It mainly consists of biology, chemistry, and physics. And broadly, if we divide this into three parts, one is energy and environment science, which is mainly the people working under chemistry. They are working on this energy and environmental science, which is related to battery, supercapacitor, and so on. Then we have a unit called chemical biology. As the name suggests, it mainly consists of the people from biological background. And I belong to a unit which name is Quantum Material and Device Unit, and we call it QMAT. And it is mainly we try to understand and design the photo. No? Okay. Okay. So what we do is that we prepare the material for your MSc course. All of you from MSc or bachelors are there as well? Bachelors as well. Okay. So bachelors, you don't have quantum mechanics, right? They do have. Okay. So basically, we work on the kind of field of low dimensional electronic system. Why low dimension? So low dimension comes from the fact if you confine any system in one of these axes, then what happens? Your energy level becomes quantized, and it gives the effect of quantization or the quantum mechanical effect. And we can also put several ingredients or masala into it. For example, if you take an electron which is moving with the velocity of light almost, and if you put an electric field in it, what will happen? Anybody? An electron is moving with the velocity of light, and you apply an electric field. Then in the rest frame of electron, what it should experience? Somebody. बोलो, गलत बोलने में कुछ तो हो रहा है, फर्क नहीं पड़ेगा, बोल दो, कुछ भी. बोलो. Magnetic field, because of the Lorentz transformation, right? Electric field will be converted into the magnetic field. So this is the idea of spintronics. So this is one of the basic idea of the spintronics. You apply an electric field, but in the rest frame of this electron, it behaves like a magnetic field. So this is coupled the electric field with the spin. Okay, so that is why it is called the spintronic instead of electronics. So the electronics is the spin. Spin and electrons are now coupled to each other. So this is what is known as spintronics. So this is a basic idea. So these are the things we are working there. So we have different area under this unit. One is the theory, purely theory. What the theory people does is number one, they predict new material. Their number one duty. Based on this theory, we try to synthesize different materials. But if theory people predict something and you prepare something, they don't match each other. Then we again go back to the theory people and discuss and try to understand what is going on. And then by doing this iteration, you try to improve the quality of the material so that you can utilize this for preparation of the devices. And in between for all this, you need what is called a measurement. So you can basically classify this into 3 or 4 this kind of subgroups. Okay, so these are the kind of achievement we have. I don't want to go into the detail of this. So this is my group especially. So this is Neha. She has finished the PhD and now joined Cornell University as a postdoc. And this is Ruchi. She has finished and joined with somebody called Professor Albert Frey, who got Nobel Prize in 2007. And Nand Kumar also finished, and he is doing working now at IIT Delhi. So if you are interested, you may look into some of our paper published in Nature Communication, Advanced Material, and so on. If you get a chance, and we can discuss also. If somebody is really interested in research, we can really talk seriously. So if after finishing your PhD, so this is so our academic affair basically consists of different stages. One is we have PhD program. This is for the PhD students. If you are interested, you can try to get into this PhD program. We also have short-term research internship. You can go to our website, choose somebody of your interest. You can send an email. If you want to work for 2-3 months, you can join and work with us. And also we have some postdoctoral research possibility as well. For those who are interested to join as a PhD, what is the criteria and how to join? You have to must have an MSc or MTech in biology, chemistry, physics, or material science. You must have a good gate on net course, very good, because it's very competitive. Usually you get around 200 applications per department, and we select around 10. So you understand it is less than 5% you get a chance to get selected. This happened twice in a year. So now let us think that life without science, this is completely impossible to think. Anything you think, you have science in it, right? So you start from healthcare unit, starting from some diseases, surgery, electricity, transport, communication, etc. Anything you think, you cannot think anything at this moment without science. So everything consists of some science. So if you ask me what exactly we do at our laboratory or what is the research you do, and my answer will be this. So this is the problem. My answer will be, we prepare 2D EG with strong Rashba spin orbit based low dimensional material for the transistor. Can anyone of you understand this? जिसको समझ में आया है वो हाथ उठाओ, because the number will be less. So this is the problem. So if you ask any scientist any question, most of the time you will get an answer which you will be unable to understand. कुछ भी पूछो, कुछ answer भी लेना, but you will not be able to understand. But today the idea will not be the same. Today I want to talk about in a very simplified manner so that most of the thing can be understandable to all of you. So basically, to understand today's discussion, you need to have idea about these two things: law of reflection and magnetic field produced by a current carrying wire. And third is law of conservation of energy. I think most of you know about this, right? So थोड़ा बता पाओगे what is the first one? Law of reflection. How many laws are there? इसमें भी 2, 3. ये तो कौन सा क्लास में है? I think this is 8 or 9. 9. तो एक फाइनल करके बताओ, 2 या 3? 3. तो 3 बता दोगे जल्दी से, if possible, क्योंकि थर्ड वाला मुझे पता चल जाएगा. अच्छा, पहले 2 से कम जो है, कम से शुरू करते हैं. 2 बता दो प्लीज जल्दी से, कोई भी है, तो एग्जाम नहीं होने वाला है बॉस. बताओ. Very good. Second is yes. Good. थर्ड वाला कोई बोलने वाले थे, वो बोल सकते हैं. थर्ड है? No. Magnetic field produced by a current carrying wire. What is the law? Savart law, Faraday law, it's kind of, you can use both. Law of conservation of energy, all of you know that energy is conserved, right? So if you understand these three, that is enough to understand today's talk. So let me start from saying the very simple thing. What is nano? Nano is nothing but 10 to the power minus 9. If it is distance, then it is nanometer. If it is time, it is nanosecond, and so on and so forth. So in case of nano, basically, this is the place where the size really matters, in a sense that if you take a bulb, if you take a mobile phone of 6 inch and 6.5 inch, it hardly matters. But if you take a nanoparticle of 1 nanometer and 2 nanometer, they appear to be very, very different. So this is the scale where it actually matters. And to give you just an idea, this one of the ideas is that if you take a human hair, and if you take the thickness of that hair, and if you can make it 100,000 times, मतलब 1 लाख बार अगर उसको काट सकते हो, वो जितना thickness देगा, that is called 1 nanometer. So you can understand वो कितना छोटे होते हैं. Anybody of you can tell me what is this number correspond to?
Diameter of Earth.
Yes, very good. Google में तो इतना जल्दी नहीं मिलेगा, बता था? Okay. Good. Anyway, very good. So this is the size diameter of the arc. अभी think of arc and think of इसका approximately 10 crore times छोटा अगर diameter कुछ करते हो, then you have an apple, right? So you can understand arc के size के respect में apple कितना छोटा है, right? And with respect to apple, nano is exactly same. So you understand nano कितना छोटे होते हैं. This is nanometer. So with respect to arc, अगर apple का size compare करो, then with respect to apple, your nano will be that size. So you understand how small a nano is. So this is a basic idea for nano. So nano versus bulk. Why nano is so important? Why everybody is saying nano, nano, nano? This is one of the examples. Let's start from this one. Take a cube of size A. So what will be the surface area? Surface area, total surface area will be nothing but 6A square. You can easily figure it out, right? And total volume will be nothing but A cube. Now, if you break it into two parts, now the surface area will be increased by 8A square. You can easily calculate because you are now producing internal surfaces, right? So you are increasing the surface area, but the volume remains constant. Now, if you divide it in 4 times, the surface area will be 24A square. And if you make it 8 times, it becomes 48A square. So you understand when you reduce the size of something, your surface area becomes larger and larger, but your total volume remains constant. What is the consequence of that? आप लोग जानते हो कि, for example, if you think of any catalyst, if you have more surface area, it can interact more and it can react much easily. So this is one of the area. For example, say you want to prepare some solar cell. If you have more surface, it can absorb more light, right? So if you make nanoparticle of the solar cell, it can give you more surface area and the efficiency can increase. So this is one of the advantage that the surface area increase is a very fundamental aspect of this nanotechnology. So I give you some ideas. So this is a very basic thing of this of taken wire which contains a current I. So if you take a perfectly this crystalline wire, that is where there is almost no defect, what happens? Your electron inside this can easily move through and without almost any resistance. So one of the reasons for the resistance which offers by an wire is because of the dislocations. If you have dislocation, then your electron, if you send the electron, it starts colliding with this, and this is giving rise to what is called the resistance. Now, if you take these 4 wires, can somebody of you tell me which one has a higher resistance? That is 4 wires. So resistance is proportional to length and inversely proportional to area. So which one has the higher resistance? This one, right? So if you make it thinner and thinner, your resistance becomes larger and larger. Okay, this is the lowest resistance. Now, when you think of preparing your laptop, computer, anything, have you ever seen any chip by yourself? कभी देखे हो ये IC chip? It consists of thousands of transistors, one chip. So you can understand उसको connect करने के लिए कितना छोटा wire use करना पड़ेगा. It has to be very, very small wire. Now you can calculate. You should try to calculate this by yourself. ये भी मैंने भी खुद से calculate किया. This is the resistance. If you take a wire of 1 unit length and you take the radius in meter, you can see that if you reduce, so this is the 10 to the power 0, means 1 meter radius, and you go down to nanometer, then you can see the resistance suddenly start increasing after 10 to the power minus 8 10 to the power 8 meter, means around 10 nanometer के बाद it start increasing and it goes to 10 nanometer में इसका resistance around 800 ohm. But when it goes to 1 nanometer, the resistance increased by 80,000 ohm. So you can calculate by yourself. Just change the radius, number उसको put करो, you can see that 1 order of magnitude change in radius change the resistance by 3 order of magnitude. So this is where the beauty of nano, that it is increasing so rapidly. And you know, when you increase the resistance, what happens? It gives rise to what is known as Joule heating, right? Higher the resistance, it gives to Joule heating. Joule heating होंगे तो your temperature of the system will rise. So this is the, so one can calculate the corresponding Joule heating, and ये देख सकते हो कि 10 to the power minus 8 मीटर मतलब 10 नैनोमीटर में इसका हीटिंग अगर टेम्परेचर अगर होते हैं 7 डिग्री सेंटीग्रेड, then if you go to 1 nanometer, इसका टेम्परेचर हो जाते हैं 78,000 डिग्री सेंटीग्रेड. And the melting point of copper is 1085 centigrade. Then everything will melt down. So this is one of the challenge, that you go down to very low size, but you keep your system stable. Okay. So how to make nanocrystal? So one of the way of making nanocrystal is that you take a solid, which is bulk, then you can break it. You can cut it or you can chip it. How long? जब तक ना तुम्हें nano size का particle मिल जाए. So this method is basically known as top to down approach, because you started from a bigger size and you break and go down to a very low size. So this is known as top down approach. There is another approach. What is that? You think of one molecule. Any idea what is the size of a molecule? Atom का size क्या होते हैं? आप लोग छोड़ दीजिए पीछे. Any idea molecule का size? 10 to the power minus 10. कहाँ से बोल रहे हो? एक बार हाथ उठा के बोलोगे. Okay. 10 to the minus 10 meter is called angstrom. So it's the angstrom order. So this is 1 order of magnitude smaller than nano, right? So you can start from one molecule. You can start combining them. Then it will become some nano size, and you can make the amount of size of this nano as much as you want. And this is, then you can prepare your nanoparticles. This approach is known as bottom-up approach, because आप नीचे छोटे से शुरू करके you are making the bigger size of the particle. The previous one was top-down approach, because you started from the big, you go down. Now it is bottom-up, because you start from smaller, you go to the larger size. Okay, so although these are the artificially made nanoparticles or nanomaterials, but you can see nano in nature as well. So in all, especially in the legs of all the insects, they are nano, typically. This is beetle, fly, spider, then lizard. They have this kind of structure, which is actually nano inside. These are their legs, actually. This is already, so nano is nothing we are creating. Nano was there in the universe before you started creating the nano. So this, all other the things which we have shown previously was the naturally nano, and these are the nanomaterials prepared by the engineers or the scientists. This is the nano structure. Okay, so and this is one of the very you all know about this example. This is if you take a lotus leaf and if you put a drop of water, it doesn't stay on the leaf, right? That is because this lotus leaf consists of many this kind of nano structure on the top of this leaf, and it doesn't allow the water to stay on the top of this. It increases the surface tension and it becomes a spherical particle. So this is naturally nano, and people have used this technology to get material or to get especially the clothes which can be self-clean. So you have this dust particle on the top of your shirt maybe, and if the water comes down, then it takes this dark particle and goes away. So this is a self-cleaning type of clothes people have started preparing using the nanomaterial technique. So this is already has been started utilizing textile technology. Okay. And also people are using the structure the shark has, because sharks are moving inside the water for a long time, but never it keep the dart on the top of this because of this kind of structure. And people are basically using this kind of structure on the top of the ship so that the ship remain clean even if it is there inside the water for a long time. So there are several examples exist naturally exist in the world. So one of the very fascinating example of nanotechnology is the electronics. Okay. So inside your computer, you have hard disk and you have RAM and ROM, right? So can somebody tell me what is the typical size of a bit or byte? Have you ever thought? लोग बोलते हैं ना कि this is a 2 terabyte or 1 terabyte. What is the meaning of terabyte? Yeah, but what is the meaning of terabyte? बोलते हैं ना कि ये hard disk है, this is a terabyte hard disk. हाँ, उतना in 1 square inch, right? So 10 to the power terabyte is 10 to the power 8. 10 to the power 8 byte within 1 square inch. Please try to calculate by yourself. Then what should be the size of 1 byte? That is remarkable. That is of the order of nanometer. तो 1 नैनोमीटर में 1 बिट रहते हैं और थोड़ा सा कंप्यूटर लेट हो जाते हैं तो हम लोग कितना गुस्सा हो जाते हैं कि लेट चल रहा है कंप्यूटर. वो चल रहा है बहुत बड़ी बात है. Okay. So this is the kind of everybody has seen this. This is the hard disk, actual hard disk. This is how it looks like. But this is an old type hard disk. This computer doesn't have this kind of hard disk anymore. It has no moving thing. And inside computer, how to store a memory? You take a magnetic material. You can either magnetize this in up direction. So there is nothing called up or down. One direction and other direction. Up का क्या मतलब है? उसको उल्टा कर दो या तो खुद उल्टा हो जाओ तो वो up down change हो जाएंगे. So there is nothing called up down. So one direction is defined as 1. The opposite direction is defined as 0. So you can put either one direction or other direction to put 1 0 0 1 and so on and so forth. And this gives rise to what is called a byte or bit in the system. So how do you do that? It's very simple. You take a magnetic material, you apply magnetic field. Then you can magnetize that in one direction, right? So what is the one of the way how to create magnetic field? How to create magnetic field? Any current carrying wire. You send current, it will create a magnetic field, right? Okay. So this is like you send current, then it is referred to magnetic field in one direction. So how to change the direction of the magnetic field? You just reverse the direction of the current, right? You change the direction of the magnetic field. So precisely this technology is used for creating. So this is a small video, not made by me. You can get it in the is available in the website. Yeah.
We visualize as a minuscule black that can be magnified to its primitive value.
Forget about this noise.
Every red, blue, or gray line.
थोड़ा सा ध्यान से देखो, then I'll let you know what is going on.
The red blacks have the north pole facing up, and the blue blacks have north pole facing down. We visualize.
Okay. So this is your magnetic strip जिसके ऊपर you want to write down the beat. Okay. And this is the magnetic pole and this is the current carrying wire. You can send the current either in this direction or you can send the current in the opposite direction. When you do that, you create a magnetic field here and you are moving this on the top of this hard disk. By changing the current, you just write down either up spin or the down spin. So this is called the write head, WRIT, not RIGST, write head, and this is called the read head. This is actually the sensor which is reading what you have written. So this is the device where you have written, this is the device by which you have written, and this is the device by which you can read what you have written. Okay. So where is nano here? As I already said. So if you take a terabyte of 10 to the power 12 byte per square inch, then what is the size? This is the size. It's nano, you cannot read, right? So the size is around 40 nanometers. You can do it by yourself. You will get a feeling. So this is a 40 nanometer size. So this is how actual hard disk works. So this is the hard disk. This is where it is writing and reading. This is the actual hard disk. This is how it works. So now the point is how to see nano. So ये तो बहुत छोटे हैं. You cannot see at all. Any idea how to see nano? Electron microscope. So, but electron microscope में आप क्या देखते हो? You have any idea? You don't see the actual particle. So you see the diffraction. Then you take the Fourier transformation to go to the real space. So आप actually में देख नहीं रहे हो. What you see is the diffraction. This is the K space. Then you take a Fourier transform to go back to the real space, right? So actually में nano आप देख ही नहीं सकते. आप देख नहीं सकते because your eye doesn't have that resolution. आपका eye visible range में देख सकते हैं, right? You cannot go to the 10⁻⁹. Your wavelength 10⁻⁹ का wavelength आप देख ही नहीं सकते. So अभी ये सोचते हैं, you think of एक elephant है और यहाँ पे you have many blind people here. How will they see elephant? They can't see, right? तो वो लोग क्या करेंगे? Some people will start touching different parts. कोई इस part को, कोई इस part को, कोई इस part को, and so on and so forth, right? तो कोई बोलेंगे कि okay, you have some kind of rope. कोई बोलेंगे कि maybe you have some wall. कोई बोलेंगे कि maybe you have some वो बड़े वाले Japanese hat, something like that. Maybe there is a sword and so on and so forth. Because they can't see, they can only feel कि okay, ये ऐसे type लग रहा है. But अगर ये बोलने के बाद भी कोई बोलेंगे maybe a pillar is there. लेकिन ये knowledge, ये जो knowledge different लोगों ने बोले हैं, if you collectively put this knowledge, हो सकता है ये उतना खराब देखने में ना भी लगे कि किसी ने वॉल बोले, किसी ने बोले कि ये है एक रोप या कोई स्नेक ऐसे टाइप का कुछ बोले. तो अगर इनको आप collectively join करोगे, it might look something like this, which is not bad. Although it's not a really elephant, but okay, it's something like an elephant, right? So in case of nano also, since we cannot see, we have to take some way so that we can realize how the thing should look like. Okay, so this is the overall idea of seeing nano. It's not really seeing nano, it's to know how it looks like. Okay. So one of the way of looking into nano, I will explain. So this is called atomic force microscopy. Have you ever heard the name atomic force microscopy? किसी ने सुना? ये front row छोड़ के, of course. because they know. आप लोग किसी ने have you ever heard? Okay, तो आप देखना चाहते हो, you come to our place anytime. We have 2 or 3 this instrument. You can come and we can show you. So this relies on what is called simply the law of reflection. It's as simple as this. How it works? So it's okay. You have a substrate. उसके ऊपर you prepare some nanostructure. Okay. Then you take a cantilever. और कैंटिलीवर के सामने ऐसे एक you have a very sharp structure. So now you shine a laser light. Laser light will fall on it. It will reflect, and you put a photo detector here. So this is angle of incident equal to angle of reflection. Now you start moving this. इसको आप move करो. So this will come from here to here, right? Then what will happen? This angle of incident is now different from angle of reflection, and this beam will now hit to different point of your detector, right? So by moving this back and forth, you can basically map out on this screen what is the point of this motion of this laser light, because this is a photo detector, and from this you can back calculate how this structure looks like. तो आपको क्या दिखाई दे रहा है? You just only see the motion of this. आपको तो ये दिखाई नहीं दे रहा. You don't see this. But from this motion, you have to get a back calculation to know how this structure looks like. So this is the overall principle of what is known as atomic force microscopy. This usually doesn't work. So this is a real-time image of atomic force microscopy. So this is the cantilever I talked about, and it wants to see. There is a very small. I don't know why it is. It wants to see this structure, so it moves back and forth on the top of this, and because of this reflection, as I said, it can basically see this nanoparticle. So this is one of the idea of the way it looks like. So this is structure of nanoparticle, nano steps. So this is the height of each nano step is around 3 nanometers, and this is not 3, 0.4 nanometer this height, and this is actually made by us, and this is the image of what is called atomic force microscopy. So from this movement of this light on the top of our detector, we take a back look and we can try to calculate how does this looks like. But one has to be very careful, because if you are not very careful in putting all the information together at right place in relation to each other, तब क्या problem हो सकता है? तब आपको हो सकता है कि हाथी के जगह पे ये दिखाई दे. You may end up with this, which has no corresponds to what you have actually. So this is one of the very crucial point, and because people are developing this knowledge for a long time to see how to see nano. Okay, so scientifically, because many of you might interested in doing research in your future, so if any of you are interested, you can look into this of our recent publication. And yes, so this is one of the this is our basically this is nothing but the postal code of our institute 160062 written on the top of a surface, and we could achieve a data density around 500 gigabyte per square inch, and this is actually written by us using a atomic force microscopy. Thank you very much. So if you have any question, please feel free to ask. My name is Shubhankar Chakraborty. Just write in Google, you can see my name. Sanjeev ji, how are you? आप आए नहीं सुनने? Yeah, if you have any question, please feel free to ask me now, or feel free to write. Please, मैं finish कर लूँ? Or you can write it to me, or नहीं तो आ जाओ. Okay, this is just here. Follow, please.
We all know that time has a different consequence in space. As the matter tends to get more massive, it tends to slow down. So does the consequence of time change in the nano world too, or even smaller than nano world?
I don't think so, because it is the idea of relativity. It has nothing to do with the size. It is only the velocity of the material which matters. So I don't think it will matter when you reduce the size. But if you reduce the size, in addition to relativity, what you get is the size छोटा होता है तो क्या effect आते हैं? No, quantum mechanics. So if you add quantum mechanics with relativity, what you get? Dirac equation. That's simple, Dirac equation. So get idea of the Dirac equation, then it comes the idea of massless and massive particle, which gives rise to what is called pair. You get the pair electron and positron, right? So this idea comes when you reduce the size. But the idea of relativity doesn't change with. Does this answer your question? Okay. So what should I have to? Partly you can ask me, you can send me email and I will try to answer as much as possible.
Any other question from the audience?
और एक दो हाथ था, but now वो डर गई है. I don't know what else. हाँ, पूछो. पूछने में कोई problem नहीं है.
My question was, how far have we come in the field of, I'd say medical applications, or rather, in the previous speakers, he was talking about the P-type semiconductors, and I had this question that is transparent conductors, and I had this question that we can maybe use it for something like internal angiography or something like that, right? If we use it in nano size. So how far have we actually come in internal imaging by using nano robots or nanoparticles?
Oh, this is very fast. This is very fast. People have started using nanotechnology for medicine and drug delivery. But imaging is fast, very fast. People have started using these nano robots, nano motors, and so on. But it's not at the stage of application. People have kind of, lot of development happened. I should not say that development has not happened yet. Lot of development happened, but it is far from real-time application. But if you think of nanotherapeutics, in using it as a marker, people are doing this lot of practical application as well. Have you know about this called what is called magnetic hyperthermia for cancer therapy? Have you ever heard? It's a very simple idea. If you take if you take a magnetic material में क्या होता है? If you take a big magnetic material, then you have what is called the domain, right? Now if you start reducing the particle size, then below some particle size it becomes single domain. एक ही domain है. Now you have the spin, all spin. Single domain मतलब क्या है? You have all spin aligned in one direction. It gives us a big magnetic moment, right? Now if you apply an AC magnetic field, what will happen? To start oscillating, right? If something oscillates, then it creates energy, right? It creates energy and it becomes hotter. If it becomes hotter, fortunately, you might know that cancer cell dies at a temperature of 43 degrees Celsius, whereas normal cells dies at a much higher temperature. So by this kind of clipping, it becomes hot and it can kill the cancer cell. So this is known as magnetic hyperthermia treatment. Okay, so this is kind of now people have started using clinically. There are many things, but as far as this nano robotics thing is concerned, not much thing has been done. Many things has been done. It's not in the practical applicability level. Yes.
Any other questions from the students? Anybody?
Anybody from faculty as well?
There is none. There is another mic we have.
You asked a question that when an electron moves and we apply an electric field, it experiences an electric force, right? And in the rest frame of reference of an electron, it experiences a magnetic force. But to experience the magnetic force, the electron has to be moving, right? But it's in the rest, in the same frame of reference.
No. पहली बात तो ये है, it's good. But you know, इलेक्ट्रॉन डेट्स कभी मत बोलना, इससे एक प्रॉब्लम होता है. बोलो क्या? It violates something.
Uncertain.
जैसे ही उसको ये confined, velocity becomes infinite. If you make the velocity infinity, zero, then it is everywhere.
But it could be moving in a random direction, for example.
Yeah, definitely.
But force is only in the one direction.
No. This electric field is not producing any. इसके वजह से वो move नहीं कर रहा है. वो खुद से move कर रहा है. Now you apply an electric field.
Okay.
Perpendicular to the motion of the electron, because V cross E is V. If it is in the same direction, then that will not produce magnetic field.
Okay.
Lorentz transformation says V cross E is the V. Right? So this is some different electric field, which is perpendicular to the direction of the electron. Okay.
Any more questions? So if there is no more question, let's thank the speaker once again. And now request Dr. Neelu and Dr. Sanjeev to kindly present token of honor to our distinguished speaker.
Yeah, sure.
Thank you so much, sir. We now have our last speaker for our technical session with us, Professor Sanjeev Kumar from Bestowed. Firstly, I would request Dr. Neelu and Dr. Sanjeev to kindly give a big welcome to our speaker. Today, Dr. Sanjeev will be talking about magnetoelectric composites, a new paradigm. Professor Sanjeev Kumar is associated with the Applied Sciences Department, Punjab Engineering College. His major research interests include ferroelectric, multiferroic, magnetoelectric composites, and nanowires. So far, he has guided 7 PhD theses, and 7 more students are continuing their work towards their PhD degrees under his guidance presently. He has published more than 150 research papers in various journals of high international and national repute. He also has acted as a principal investigator for many research projects funded by various agencies. We are truly honored to have you with us, sir. I would now request Dr. Sanjeev to kindly continue his talk.
Hi, good afternoon to all of you. First of all, I would like to thank the organizers for giving me the opportunity to interact with you people, right? So I am always finding some way to interact with you because somehow I don't know the students from these bright colleges. They went to some universities or other places, but they don't come to Punjab Engineering College for PhD. So I want that you should come to our lab and you can see the facilities, what we are doing. And I am going to what we can say. Recently, I got one DRDO project, and I need one student with GATE or NET, only NET
can be preferable. So I will share the things with Dr. Sanjeev, and he will share the things with you, right? So it is a good project, and we can provide you the fellowship for 3 years. So in this way, I want that you people should come to our lab. You can see. And second thing I want to say that it's a wonderful auditorium. So I have seen it first time because Sanjeev invited me this for this auditorium. But it's really a wonderful auditorium because I am also organizing few workshops or other things, but I am not able to get such a beautiful auditorium, comfortable auditorium. Okay, fine. So with this, let me start the topic, that is the magnetoelectric composites. So magnetoelectric composites, in which I will give you some glimpse about the composites of ferroelectric and ferrite materials. So first of all, what is ferroelectric? So I think you have seen the piezoelectric material. Do you know about piezoelectric? कहाँ यूज करते हो आप लोग डेली लाइफ में? कहाँ यूज करता है कोई piezoelectric? अरे वाह, ये यूज करते हैं. कहाँ यूज करते हैं आप?
My dad has a business of medical machinery. German machine. So we provide shockwave therapy using piezo crystals.
Oh, very good. So I will interact with you after this lecture. Fine. Any other? Yes. कहाँ यूज करते हैं भाई? Crystal oscillator. Okay. अरे ये हुई ना बात. हाँ, ये गैस लाइटर आप शर्मा रहे हो, सिगरेट लाइटर की तरह भी यूज करते हैं, right? But it's really a gas lighter. Yes, yes. So everybody is using that gas lighter. So that is a piezoelectric, right? Even though in earlier days, जो बाइक में आप लोग किक मारते हैं इंजन स्टार्ट करने के लिए, वहां भी एक पीजोइलेक्ट्रिक क्रिस्टल रहता है. तो आपके प्रेशर से वोल्टेज स्पार्क जनरेट होता है और वो आपके इंजन को फर्दर स्टार्ट करता है. So that is about the piezoelectric material, right? Second thing, these piezoelectric materials, most of them they are ferroelectric also, right? So I think you have some idea about the ferromagnetic materials, right? Ferromagnetic सुना है कभी? सबने सुना है, सबने पढ़ा भी होगा डोमेन, right? जिसमें आपके spins they get aligned in one particular direction. I think you have all have that idea. So on the same basis, in the ferroelectric materials you have electric dipoles. वहां पर क्या था? नेट मैग्नेटिक मोमेंट स्पिन का रोल रहता है. यहाँ पे क्या होता है आपके पास? इलेक्ट्रिक डाइपोल. If you want to create electric dipole, what do you have to do? Suppose if you have some material in which you have atoms, right? Some of the materials are polar. Polar means they have already electric dipole, and some of them are non-polar, right? So if you want to generate a dipole, क्या करेंगे आप? Yes, you have to apply electric field. So your atom initially it is a neutral, right? So in the atom you have a nucleus in which you have protons and neutrons, and in the surrounding you have electrons orbiting, right? So in the nucleus you have positively charged protons. Because of that you have a center of positive charge, and you have a center of negative charge because of the revolving electrons. If both center of positive and negative charges they are merging with each other, then the net dipole moment is 0. But if you apply electric field, what will happen? Under the application of the electric field, your electron cloud and your nucleus is a heavy one, because your protons and neutrons they have very high mass as compared to electrons. So there will be separation between the center of negative and positive charge, and that will create an electric dipole, right? So in this manner you can generate an electric dipole. Okay. Second one, okay. So nowadays piezoelectric materials, people are trying to harvest the energy using those piezoelectric materials, right? कैसे कर सकते हैं हम लोग हार्वेस्ट एनर्जी? एक वेट मेजर करने की मशीन भी होती है ना? आप लोग वेट मेजर करते हैं उससे, वो भी piezoelectric based ही रहता है. There is a pressure sensor basically, right? So if you are applying some pressure, it will generate some energy. Okay. So this one is the first example. That is the simple gas lighter or the cigarette lighter. Second one, to harvest the energy using these piezoelectric materials, if you put that material in the sole of your boot or shoes, what will happen? Whenever you walk, you are applying some pressure. right? So when you are applying some pressure, yes.
I did this project in, I think, 7th standard in my school.
Good. So how much energy you have stored? अच्छा बल्ब जलाई थी. गुड. तो उसको शूज में लगा रखा था जब भी चल. अच्छा, गुड, वेरी गुड. But nowadays people are trying to somehow get these materials in this form, and these materials will be able to charge your small electronic gadgets, not the bigger one like your smartwatch or your mobile phone. So it will be helpful in somehow. Second one, you can use them in dance floors, right? डांस करके एनर्जी वेस्ट कर रहे हैं अपनी, बट वो एनर्जी जहां वेस्ट कर रहे हैं वो आप पीजोइलेक्ट्रिक टाइल्स पे डालो तो कुछ वोल्टेज तो जनरेट करेगा वो, है ना? So these are the piezoelectric tiles basically, on which you can apply the pressure and you will generate the energy, and further you can use it. So like in a vehicle, you have number of piezoelectric materials, not single one. There are different types of sensors in which you are using the piezoelectric materials, right? So this is the basic structure that I want to show you. I think most of you are from MSc Physics background. Is it so? Right. So do you have some idea about this barium titanate? Thank you. Do you have some idea about barium titanate? कोई एक्सपेरिमेंट करते हैं आप लोग कुछ ट्रांजिशन टेम्परेचर फाइंड करने के लिए? नहीं किया. ओके, कोई बात नहीं, डोंट. So this is the simple structure of a barium titanate. So barium titanate is a material that is a ferroelectric material. So pointer, this is the pointer. Are you able to see? Yes. Okay, fine. So these red atoms are of barium and these green atoms are of oxygen and this blue atom is of titanium, right? So it is a simple cubic structure. In the barium you have +2 charge, and in the titanium you have +4 charge, and in the oxygen you have -2 charge, right? And because of this cubic symmetry, the net charge is 0. It means what? It means the center of positive and negative charges, they are merging with each other and there is no net dipole. But usually this titanium atom that is at the center of this cube, it is not at rest. It is always in vibrating. It is always in vibrating motion, right? So when it will move upwards, what will happen? To balance the things, these oxygen atoms will move little bit downwards, and because of that, the center of positive and negative charges, they get separated, and you have the generation of an electric dipole. But why it is so? Because one of the dimension is increasing. Now this structure is the cubic one. This one is the cubic, and this one is the tetragonal, right? Which side got elongated? This one, right? Because of the movement of the atoms. The movement is very slight, right? But still, because of that small movement, you will have this type of changes. So in this manner, because of the structural dependence, you have electric dipoles. Okay. So in the ferroelectric materials, basically, they exhibit the similar loop between the applied electric field and the induced polarization as that of ferromagnetic materials. Ferromagnetic materials में आप क्या करते हैं? You apply the magnetic field and you will have the induced magnetization, right? And in the ferroelectric, you have to apply the electric field and you have induced polarization, right? And you will get this type of similar hysteresis loop, right? So most of these ferroelectric materials, as they are also piezoelectric materials, but these materials are lead-based materials. So lead is what? Lead is toxic in nature, right? But ये हमारे लिए ही है. जितनी फॉरेन कंट्रीज हैं वो सब लेड यूज करती हैं. वो हमारे पर रिस्ट्रिक्शंस लगाते हैं कि यहाँ पे लेड यूज नहीं करना. तो मैंने भी अपने पीएचडी स्टूडेंट को लगाया हुआ, बैठा है यहीं पे वो, लेकिन वो जरा कर नहीं पा रहा कुछ उसमें लेड में. So but still they are imposing restrictions on countries like us, right? But they are enjoying the benefits of this lead-based material. And they are saying, no, you cannot work on lead-based materials. You have to work on lead-free materials, which should not be toxic in nature, right? They should be environmental friendly, right? But somehow we are able to use that lead-based material also. We are trying to work on that because our defense system requires a lot of applications. I hope you know about the DRDO labs. How many DRDO labs are there in Chandigarh? DRDO means Defense Research and Development Organization. How many labs we have in Chandigarh? Any idea? 2. Good. Which one? But good. 2. One is TDRL, Terminal Ballistics Research Laboratory, and it has a space of 5,500 acres. 5,500 acres. That is in Ramgarh, right? Ramgarh range. You take office 30 minutes, but their actual field is in Ramgarh. That is in Panchkulam. Second one is Sector 37. क्या बोलते हैं उसे हम? Yes, Sase, snow avalanche and infrastructure, right? So we have 2 DRDO labs, and they required these type of materials a lot, right? क्योंकि जैसे suppose कोई blast होता है, कहीं कुछ explosion हुआ, right? चलो मैं आपको इस interesting में हम लोग बात करते हैं जो काम किया, that is different thing. Suppose if there will be some explosion, what will happen? If you are 100 meters from the explosion, but still you will feel some pressure waves. Those waves are known as shock waves. Those waves are known as shock waves, right? ये जितने भी नक्सली हैं, जो लोग हैं, वो क्या करते हैं? माइन्स लगा देते हैं, और जब भी हमारा मिलिट्री का कोई व्हीकल उसपे से जाता है, तो माइन एक्सप्लोड करती है, एंड दे विल बी, मतलब वो डैमेज हो जाता है सारा कुछ. So what the DRDO people are trying, they are making the vehicles with some hull. Hull means a metallic body below the vehicle, so that if the explosion will be there, then its effect will be bifurcated in this manner. तो जो अंदर लोग बैठे हैं, somehow उनको कम से कम प्रॉब्लम आए, right? इस तरह के व्हीकल पे ये लोग काम कर रहे हैं, TBRL वाले, and they have been authenticated. They are giving some certifications to Tata Motors also, because they are the developers. वो सब कुछ यहाँ पर करते हैं, आके टेस्ट करते हैं, ब्लास्ट करते हैं, देखते हैं कि vehicle is tested or not. But what they observe in Telangana, now Telangana, there is some vehicle with that hull. Hull means a metallic base, right? In this manner, below the vehicle. So that whenever there is an explosion, the explosion effect will be bifurcated in this manner, right? It will not directly affect the people sitting in the vehicle. But what they observed there was some explosion, but all the personnel, CRPF persons, they get injured. Injured not means they got dead. So what is the reason? कुछ लगा नहीं है उनको, वो व्हीकल के अंदर व्हीकल एज इट इज है, एक्सप्लोजन हो गया है, ठीक है, वो दोनों तरफ फैल गया, बट जितने भी लोग अंदर बैठे थे सब मर गए, उसमें कोई भी खरोंच नहीं आया, कुछ नहीं आया. तो वो क्यों हुआ? बिकॉज ऑफ द शॉक वेव्स. जो शॉक वेव्स का प्रेशर होता है एक्सप्लोजन के बाद, जो इसमें प्रेशर से शॉक वेव आती है, वो आपके लंग्स को पंक्चर कर देती है, एंड बिकॉज ऑफ दैट पंक्चरिंग ऑफ लंग्स, राइट, वो अंदर से ब्लीडिंग स्टार्ट हो जाता है, एंड द बॉडी, राइट. So these people, they require these materials, right? Why? Because they are pressure sensors. Piezoelectric मैंने आपको बताया कि अगर आप फोर्स लगाओगे, there will be some voltage generation. तो जितना आप फोर्स लगाओगे, उसके correspondingly compliance में अगर आपको वोल्टेज मिलती है, you can generate some pressure sensor, right? आपने इतना प्रेशर किया, and you can sense that what amount of pressure is there, right? So these materials are very much required for our defense people, right? And they are trying to get the people indulged in this particular area. Otherwise, whatever, there is a monopoly of some agencies outside. What they are doing, they are manufacturing the sensor, and they are costing those sensors as their monopoly. Means whatever the cost they want, वो हमें लेना ही पड़ता है, क्योंकि हम लोग खुद नहीं बना पा रहे हैं, right? Because of that, our Prime Minister nowadays is focusing on Make in India. So they are trying, but still there are lack of facilities to develop such sensors. But somehow, if you young people, they can come, they can think over it, right? then we will be able to develop the things in our own country. Otherwise, हम लोग जो 50,000 की चीज है वो 5 लाख में खरीद रहे हैं, तो 4.5 लाख कहाँ जा रहा है? बाहर जा रहा है, राइट? और इन दिस मैनर वी आर नॉट एबल, जो हम लोग बोलते हैं कि वी आर नॉट गोइंग अबव द पॉवर्टी लाइन, तो पॉवर्टी तो रहेगी ही रहेगी, राइट? ओके, सो आई हैव टॉक्ड, ओके। सेकंड थिंग, इसमें बैक कैसे जाएंगे? चलो कोई बात नहीं। सो इन योर मोबाइल फोन यू हैव पीजोइलेक्ट्रिक सेंसर? यस, कौन कौन से सेंसर? मोबाइल फोन में सेंसर तो पता होंगे आपको कौन कौन से होते हैं। आप चलते हो, पैदल चलते हो तो आपके वो स्टेप्स काउंट कर लेता है ना? और कितने तरह के सेंसर्स होते हैं? बड़े तरह के सेंसर, प्रॉक्सिमिटी सेंसर भी होता है, हाँ, गायरोस्कोप सेंसर होता है। देयर आर नंबर ऑफ सेंसर, राइट? बट जो आपका स्पीकर होता है वो कैसा होता है? जब आप स्पीकर ऑन करते हो आपको आवाज आती है स्पीकर। आपने पुराना स्पीकर देखा, एक मैग्नेट होता था, मैग्नेट के ऊपर एक डायाफ्राम होता था, राइट? तो अब वो इतना बड़ा मैग्नेट तो नहीं होता हमारे मोबाइल में, वो किस तरह का स्पीकर होता है? कुछ आइडिया? दैट इज आल्सो पीजोइलेक्ट्रिक बेस्ड। सो यू आर अप्लाइंग द इलेक्ट्रिक सिग्नल एंड इट इज वाइब्रेटिंग, राइट? जैसे मैंने बताया आपको कि पीजोइलेक्ट्रिक में क्या होता है कि यू आर अप्लाइंग सम प्रेशर, यू आर जनरेटिंग सम वोल्टेज, बट द कन्वर्स इज आल्सो ट्रू। इफ यू आर अप्लाइंग सम वोल्टेज, इट्स डायमेंशंस विल चेंज, राइट? अल्ट्रासोनिक वेव्स क्या होती हैं? व्हाट आर द अल्ट्रासोनिक वेव्स? The whose frequency is above 20,000 hertz, right? To generate such high frequency waves, you need these piezoelectric materials. You apply the electric signal at that frequency, and the piezoelectric material will vibrate at that frequency. It will generate those waves. Okay. So now I will tell you something about this. That is the multiferroic material. Nowadays, people are working on this multiferroic material. So multiferroic material is basically the combination of a ferroelectric and ferrite material. अच्छा, first of all, what is ferroelectric? Do you have, जो मैंने आपको बताया, कुछ आइडिया लगा? फेरोमैग्नेट आपको आइडिया है? So on the same basis, you have ferroelectric, in which your electric dipoles are playing the same role as that of the magnetic spin, right? So if you are able to combine a ferroelectric and ferromagnetic material in a single phase, those type of materials are known as multiferroic materials. अच्छा, एक चीज मुझे बताइए, आपको अगर इंसुलेटर चाहिए या डाइलेक्ट्रिक चाहिए, तो उसके आउटर ऑर्बिटल्स कंप्लीटली फिल्ड होने चाहिए एटम के, कि दे शुड बी हाफ या पार्शियली फिल्ड? If you want some dielectric with good insulating properties, then the outermost shells of your atom, they should be completely filled or partially filled or half filled. हाँ ठीक बोल, हाँ नहीं half filled, अच्छा वो कुछ बोल रहे हैं, completely filled or either empty, right? Right, it's correct answer, right? और अगर आपको magnetic material चाहिए, then partially filled, because the unpaired electrons, they will contribute to the net magnetic moment, right? So these two materials are entirely different. Ferroelectric is a dielectric material, right? So ferroelectric and the ferromagnetic or ferrite material, they are entirely different. One requires the half or partially filled shell, and another requires the completely filled or completely empty shell, right? So how you will get the combination of these two? So there are some materials in which the electron motion in the orbit, that will serve both the purposes. Means for some time it will be serving as a completely filled, and sometimes it is for some time it is serving as partially filled. So there are few materials like bismuth ferrite which are showing these kind of properties. But the problem with that material is that it is very difficult to synthesize that, right? So I am coming to the material which, so I am not going into this one because I want to tell you something basics. Okay, yeah. So you have a piezoelectric material on which you are applying a pressure, you will generate some voltage, and you have a magnetostrictive material. What is magnetostrictive material? When you apply the magnetic field, its dimensions will change. Its dimensions will change. That is a magnetostrictive material, right? So in this you can see Okay. So I think I am audible. Right. So this is a magnetostrictive material on which when you apply the magnetic field, there will be some strain, right? And this is a piezoelectric material on which you apply some pressure, there will be some voltage generation. If you combine these two materials in this manner, right, there is a separate layer of a piezoelectric material and a separate layer of a magnetic material. And there is an interface between the two materials, right? What will happen if you have a composite of a piezoelectric and a magnetic ferrite material, and there is an interface between the two materials? So what will happen? There is some interface, correct? So when you apply some voltage or when you apply some magnetic field, let us say you have a composite and you are applying some magnetic field, external magnetic field. What will happen? The magnetostrictive material, it will be influenced by the external applied magnetic field and its dimensions will change. But it is connected with the piezoelectric material through the interface. So when its dimensions will change, it will affect the piezoelectric material. And because of that, there will be some strain transfer from ferrite or magnetic material to the piezoelectric material, and that strain will generate some voltage. So by applying the magnetic field, you are able to generate the voltage, right? By applying the magnetic field, you will be able to generate voltage, or vice versa. If you are applying some pressure, there will be, if you are applying some voltage, there will be some strain in the piezoelectric, and that will be transferred to the magnetostrictive, and because of it, its magnetization, that will be changed. So by applying one field, you can play with two materials, right? You are applying a magnetic field, right? It will change the dimensions of the magnetostrictive material, and that strain is transferred to the piezoelectric material, and you will have some generation of a voltage, right? So that is the beauty of these magnetoelectric materials, that you can apply one field and you can play with the two materials. Okay. So we have the facility in our lab through which we can measure this coupling. There is a coupling basically, right? There is some coupling because your strain is transferring from the interface to the next material. So there should be some coupling through the interface between the two materials. So how strong is your coupling? That will make the material more important. If it is not so strong, then there is some problem at the interface or in the material. So you should be careful about the interface. So in our lab, so I am coming to the particular one. Yes, we have developed these type of material. So here you can see the upper one is the ferroelectric material and the lower one is the ferrite material. So let me tell you the full form. This BCZT, barium, calcium, zirconium titanate. It is a ferroelectric material. NZFO, nickel, zinc, ferrite. It is a magnetic material, right? And we have pasted these two materials with silver epoxy. So this is a bilayer composite and this is a tri-layer composite. तो इसको हम लोग कैसे कैरेक्टराइज करते हैं? पहले हम लोग इलेक्ट्रॉन माइक्रोस्कोप पे जाके उसका ग्रेन साइज देखते हैं कि हमने जो बनाया मटेरियल उसका ग्रेन साइज कैसा है, हाउ इट इज बिहेविंग, and what is the random distribution of the grain, and then we go for the X-ray XRD, that is X-ray diffraction, right? So I hope you have some idea about X-ray diffraction, right? So why you use the X-ray diffraction? To study the crystal structure, right? So it is very important for us to study the crystal structure before further characterization, right? So, okay. Then after that, we have measured the dielectric properties of the material, that how its dielectric behavior is there. Then we measure the polarization versus applied electric field, right? Acha, ek cheez, your magnetic material is conductive in nature because it has unpaired electrons, right? But your ferroelectric or a dielectric material, it is insulating nature, right? Because it has no free electrons, right? And now you are making the composite of these two materials, right? So you are applying some magnetic field or you are generating some voltage. So there should be no conduction because you're measuring the voltage, right? So that's why we have took the ferromagnetic material as separate one and the ferrite material as separate one. Otherwise, अगर वो combination हो जाएगा तो ferrite के through आपका conduction possible हो जाएगा. Your electrons can move from one point to another, and you are not able to generate the as desired voltage. So this facility we have in our lab through which we can measure the coupling between the two materials. That is known as magnetoelectric coupling, and its coefficient is represented as alpha, whose units are millivolt per centimeter Oersted. So along y-axis, you are applying the magnetic field and you are observing this coupling coefficient along the y-axis, right? So in this manner, we measure the magnetoelectric coefficient in our lab. Okay, fine. So besides this, nowadays, one of the PhD students, she has developed this particular composite with the varying thickness of the material, and she observed the self-biasing phenomenon. Self-biasing means just you have a composite, right? You are not applying any magnetic field, but still you have some voltage. That is known as self-biasing phenomenon. So now I want to show you some of the facilities we have in our lab. So we have impedance analyzer with us, through which we can measure the dielectric properties with temperature and frequency. And we have the sample holders for bulk material as well as thin film material. And even though we can measure the entire temperature range from liquid nitrogen to 500 degrees C, through which you can measure that how your crystal structure is changing with temperature. We have this LCR meter with also in our lab, through which we will measure the magnetodielectric properties. This is the ferroelectric unit we have, through which we can measure the loops between the applied electric field and the induced polarization. This is the electrometer we have. This one is the electrometer, through which we can measure a very small amount of charge in picocoulombs also. We can measure the charge developed on the sample. And this one is the piezoelectric coefficient measurement unit. It will tell you that how effective is your material, piezoelectric material, and it measures some values in the units of picocoulomb per Newton. Picocoulomb is the unit of charge and Newton is the force. So how much force you have applied and how much charge you have generated. That we can measure. And this is the electromagnet we have with 1.5 Tesla magnetic field we can generate between the poles, right? And that is the spin coater used to generate the thin film. This is the machine through which we can convert the powder in the form of pellets to characterize these materials. These are the furnaces used for the calcination and sintering of the material. These are again the furnaces. This is again a high temperature furnace. It can go up to 1700 degrees C. And this is the ball milling unit we have, through which we can mix the powder, right? Because there are different techniques, but one technique that is known as solid state reaction technique, in which just you have to mix the powder and you have to rotate the powders at very high frequency. So with that rotation, there will be some chemical reaction and the desired compound you can get. This is again lock-in amplifier with the electromagnet, through which we can measure the magnetoelectric voltage in our lab. So with this, in the acknowledgements, I would like to thank the DSP, DRDO, and my institute for generous funding, and my PhD students who are doing work day and night, and I am here to present their work. So with this, thank you. So now if you have some questions, you can ask, please.
Any questions from the audience, please?
So first thing is, whenever you will get time, you can come, you are welcome to our lab, right? And try to do PhD, right? If you wish. So we have very good facilities and I need the good students. That's why I'm here. क्या please? गेट क्वालिफाई होना चाहिए बट मास्टर्स भी कंप्लीट होना चाहिए. हाँ, मास्टर्स एक्चुअली में प्रोजेक्ट सेक्शन हो गया, बस वहां से पैसा रिलीज होना है. जैसे वो रिलीज होगा तो आई विल एडवर्टाइज द पोजीशन. Project on bismuth ferrite barium technique, high temperature piezo. Yes, because they want the sensors to be used in the aero engine. Because जब वो move करते हैं तो काफी temperature generate होता है, उसमें vibration control देखने के लिए वो sensor. So we are just going to develop the material, high temperature piezo. Yes. Yes.
Any other question from the audience? Okay, if there are no more questions, let's thank the speaker once again. And now we will our worthy principal sir, Dr. Ajay Sharma, to kindly present a token of honor to our distinguished guests. Thank you so much, everyone. We have come towards the end of our function. Before we conclude our event, we would like to distribute prizes for some competitions that were held by the board on in collaboration with Deen Campus Committee and the Environmental Society Haridima of the college. The first competition was declamation competition. The prizes for this event are in the B.Voc from our college only. I would request Dr. Neelu, Dr. Sanjeev, and our worthy principal sir to kindly give away the prizes. And of course, our distinguished guests as well. In the B.Voc. Next prize, Jagriti Sharma from Punjab University, Chandigarh. Next, third prize, Tanya Spolia from our college only. The next prize, the next competition was PowerPoint presentation. The first prize for this, again, Jagriti Sharma from Punjab University, Chandigarh. I guess she is on her way. The second prize is for Pihu Works from our college only. Third prize, Ishita and Shivani Mishra. Next, we have prizes for the poster making competition organized by Department of Zoology in collaboration with Deen Campus Committee and Haridima. The first prize goes to Nandini, BSc third year medical. Please give them a huge round of applause. The second prize goes to Avneet Kaur, again BSc third year. Third prize goes to Tripti Dang, BA third year. Tripti Dang, BA third year. Okay, along with the event, you all are aware there was a poster presentation event held today in our department. So we have prizes for the best poster award. The first prize goes to Mr. Rajendra Singh from Punjab University, Chandigarh. All of you know him. Second prize goes to Miss Mehak from Penn. Miss Jagrati from Punjab University, I guess she has reached. So she has prizes for 2 events. Jagrati, please come up the dial. She was first in the PowerPoint competition and she secured second prize in the declamation competition, which were organized on the Akshay Urja Day. There are 2 prizes for her.
You have 2 prizes.
Thank you so much, everyone. I now request our worthy principal, Dr. Ajay Sharma, to kindly present a formal vote of thanks.
4 बजे हॉल भरा हो तो इससे ज्यादा खुशी को हो नहीं सकती है, और वो भी एकेडमिक प्रोग्राम। कल्चरल प्रोग्राम हो तो शायद रात को 10 बजे भी बच्चों को निकालना पड़ता है, बट और उससे ज्यादा खुशी ये है कि हंस रहे हैं, सोए नहीं हुए हैं। तो इस वीक के भाई स्पीकर भी अच्छे थे और स्टूडेंट तो अच्छे हैं। सो कुछ रियलिटीज का टीचर्स को पता ही होता है, और पोस्ट लंच सेशन में खास तौर पे, keeping in mind that you are all smiling, it is a success of the program. And you know, though colleges are mainly here for the academic pursuit, for research and training and the human resource development, but certainly the programs are need of the hour and they are less in number. Though collaborative approach, experiential learning, and practical approach is a need of the hour, and we need to have more and more of this. And certainly, I feel that after a lot of deliberations, the students must be aware of that what latest and recent is happening in this world. Though our faculty of department is also working hard in this area and they are having their own expertise, but no one is perfect. You must feel that with this age of development, everyone is having its own specialization, and that specialization is more from micro specializations. So we must always try to learn more and more, and in that way, having the expertise from our other institutions is in need of the hour. And particularly like Professor Saab was talking about the facilities and PAC and everything. Now the government is also looking at an approach that we should be in a position to have optimal utilization of resources. You may find out that in certain labs, certain things are available in abundance, and other one there is a shortage. So if we can use our resources, we can pool our resources, that way we will be in a better position to serve the society. So one of the reasons to have a CRIC here with the core competence from the different universities, including Punjab University, NIPER, IMPACT, PAC and everything is the same. So sometimes we feel that instead of investing too much and which is not utilized later, it is better to utilize the resources. And that's true not only for infra, it is also true for our brains also. You can find out that there is so much of the human capital available, but we are not, because we are not combining, we are not collaborating. So there is a lot of unutilized capacity. So somewhere I feel that we should engage more and more for research, for publication, for technology transfer, for patents, for IPRs, and for entrepreneurship also. And not only in science field, even because these are the days of interdisciplinary learnings. So we can use the aspect of the other department also, like our college is multidisciplinary in nature, having presence in the IT also, biosciences also, commerce, business management, humanities, liberal arts, and there is a lot of potentials available. But these days, we are not sharing. That's why we are not having better research publications, better developments. So I request all of you that let's move further also. Like we started today with Sanskrit and physics in the morning. Certainly, I was asking Devi sir, where were you? हमारे संस्कृत जो HOD हैं, कि आपका तो फिजिक्स में आज बहुत जरूरत थी, तो मेरी शक्ल देख रहे थे, क्या हो गया? मैं कहा आप टीचर से पूछना क्या हो गया? But certainly, it is a reality today that government is looking towards interdisciplinary realities. So while we are organizing the program, so I will request the madam that in future let's involve at least those related fields also. तो अगर आज केमिस्ट्री, बॉटनी, बायोलॉजी वाले भी बैठे होते तो मजा मुझे आ रहा। आई एम नॉट सेइंग कि भाई प्रोग्राम कोई बुरा था या कुछ वो था, लेकिन certainly these are all interdisciplinary realities, so we should try to engage others also. But well done, good program, well organized, and keep doing good work. Thanks a lot.
Thank you so much, Principal Sir, not only for sparing your time, but also being ever supportive and ever encouraging. I now request everyone to please join us for a group photograph with Sir. जैसा सर आपको ठीक लगा।
क्या नाम है, खाली इनको बोलो किसी का फोन रह गया है टीचर्स में।
क्या यार पॉइंट ऑफ ये रखो।
एक सिंपल ऐसे जो भी करना है तो खाली
नीचे
फोन वहाँ टेबल पे
फोन नहीं है ना,
मेरा फोन ही नहीं है।
ये बताओ।